Hi students, good evening. Today NEET exam 2022 was conducted all over India. And now we are going to discuss the questions from chemistry. Okay. We will start from the 51st question, which is the first question from chemistry. Choose the correct statement. 1. Diamond is sp3 hybridized and graphite is sp2 hybridized. They mean the carbon atom in diamond is sp3 hybridized and graphite is sp2 hybridized. We know it's a correct statement. 2. Both the diamond and graphite are used as dry lubricants. That's wrong. Only graphite powder gives microcrystalline structure upon powdering, and that only can act as lubricant, not diamond powder. You cannot think of diamond being used as a lubricant, the costly diamond. So that's a wrong statement. Diamond and graphite have two-dimensional network. Again, all of us know, I think without any exception, all of us know, graphite has two planar or two-dimensional structure. Of course, it is stacked to three dimension, that's true, but it is having planar arrangement of its atoms. Okay. Whereas diamond, we know, being sp3 network, sp3 hybrid tetrahedral structures, interconnected tetrahedral structures results in three-dimensional structure. So, that's another correct statement. Last, fourth one, diamond is covalent and graphite is ionic. We know, all of us know, diamond as well as graphite involve covalent bonds only. So, that statement is also incorrect. So, first statement is correct. Second statement wrong. Third statement wrong because diamond is having three-dimensional geometry and graphite is having two-dimensional structure. So, that's also wrong. Diamond is covalent and graphite is ionic is also wrong. So, for the very first question, the very first option is the correct answer. 50. Okay. Now, the next question, question number 52. Which statement regarding polymers is not correct? Which are the statements? 1. Thermoplastic polymers are capable of repeatedly softening and hardening on heating and cooling respectively. Yeah, that's the very basic nature of thermoplastic, that it can be molded any number of times because they can be softened by heating and hardened for the cooling. So you can reuse it any number of times, we know. 2. Thermosetting polymers are reusable. No, we know. While we prepare thermosetting plastic, large degree of interconnectivity among molecules give rise to a hard, unbreakable, non-fusible material like bakelite, and so we cannot remelt it and reuse it. Okay. So that statement, the second statement is incorrect. Third, elastomers have polymer chains held together by weak intermolecular forces. We know elastomers have the weakest force among polymer strands, the weak van der Waals forces among the strands. Okay, so they have comparatively low melting point to elastomers. Okay, and lastly, fibers possess high tensile strength. Yeah, upon a fiber strand you can hang heavy weight, suggesting that they have high tensile strength. That's also true. So this statement is not correct. Second statement. So first question, 51st question. First one is the answer. 52nd question. Second one is the answer, that thermosetting polymers are reusable. That is wrong. Okay. Next question, question number 53. Based on a set of graphs, which of the following PV curve represents maximum work done? Okay, these are the 4 plots given. Are all these plots genuine? That's the first thing we have to verify. See, all these plots are isotherm. Okay. In all plots, y-axis have pressure and x-axis as volume as variable. And also we must imagine that pressure and volume are marked on the same scales in all these plots. You cannot have 1 units of volume in one plot and another set of unit of volume in another case. So all are plotted with the same pressure unit and same volume unit in all the plots. Okay. Look at the first plot. Here volume is not at all changing. When pressure is increasing, volume is not at all changing. You have to also remember all these studies are based on the same amount of gas. Okay, that also we have to remember. And the temperature is also a constant since they are isotherms. So N and T are constants. Then what are the two remaining variables P and V? If N and T are constant, we know when P increases, V must decrease. When V increases, P must decrease. But here what is happening? P is changing, but volume remaining a constant. For an isotherm, that is not possible. Okay. Now this kind of variation is possible because it is isotherm. When pressure is increasing, volume is decreasing. But again coming over the third one. Look here. Here for the same pressure, you will have two volumes for an isotherm, which is another impossibility, isn't it? For the same pressure at same temperature for the same given amount of gas, you cannot have two different volumes. So this is also a case of impossibility. Now these two are possible. Since in these two plots, pressure is also changing along with the volume, we must consider them as reversible cases of expansion or contraction. Okay, it can be, both are reversible. And for reversible processes, work done is equal to minus 2.303 nRT log V2 by V1. Minus 2.nR3 log V2 by V1. In this case, what is delta V? This. What is delta V here? This much. So, V2 by V1 is greater in one case and smaller in the other case. Here V1 we can take as this. Okay. V2 this. Here V1 this, V2 this. So delta V is large for in this case, small in this case. So work is equal to minus 2.303 nRT log V2 by V1 is greater for this. Here we are bothered only about the magnitude of the work, so don't bother about the negative side. Because it is not mentioned whether work is, whether we are considering work done by the system or on the system. So we need bother about the magnitude only. So we can conclude that maximum work is done in this case, the fourth case. Okay, hope you followed that. Question number 54. The Gildahl's method for the estimation of nitrogen can be used to estimate the amount of nitrogen in which one of the following compounds. And they have listed a set of compounds. If you remember, in Gildahl's method, we cannot estimate nitrogen present in a specific set of compounds. Which are they? Please remember, they are when nitrogen is present as a diazonium salt, okay, as in benzene diazonium chloride, like that, or as a diazo compound, okay, like this, diazo compound, or when nitrogen is part of a heterocyclic ring, like this pyridine, nitrogen part of a ring. Or other nitro compounds like nitrobenzene, nitroalkane, etc. You have to bear this in mind. When nitrogen is present as a diazonium salt or as a diazo compound, or when nitrogen is a part of a ring, or when nitrogen is present as a nitro or nitrite. In all these cases, nitrogen will not get converted to ammonia and then become ammonium sulfate when we try to gelidolize the organic compound. So all these compounds will not answer Gelidol's method. It will not report. Okay. So now look at the given options. Benzenamine or aniline. Yeah, it will answer. Then we have diazobenzene. No, this will not answer because it is in this list. Third, nitrobenzene. Again, that will not answer. It is in the list. This, brilliant. It will not answer. Again, that's in the list. So, except this one, none of the remaining options can be valid. So, here for question number 54, our answer is very much 1. Aniline. Okay. The next question, question number 55. Two statements are given. You have to verify the validity of the two statements and say whether both are correct, both are wrong, one is correct and the other is wrong. Okay. It is from surface chemistry. First statement, coagulation power on a negative, see I am not reading the whole question as such, but the implication of the question I am reading. Statement 1, coagulation power on a negative colloid, means negatively charged colloid. When we say negatively charged colloid, you have to remember that colloids are electrically neutral. When we say negatively charged colloid, we simply means phase particles are negative charge and medium is positive charge. The charge of the colloid is known after the charge of the phase particle. That's why it is called a negative colloid and a positive colloid. We know that. Okay. Coagulation power on a negatively charged colloid. We know a negatively charged colloid is destroyed by as per Hardy-Schulze rule. A negatively charged colloid is coagulated by positive ions in the electrolyte, added electrolyte, and a positively charged colloid is coagulated by negative ion of the added electrolyte. Okay. Further, greater the number of charge per ion, greater the ease of coagulation. Easier will be the coagulation. Okay. Look here. Coagulation power on a negatively charged colloid follows the order Al3 plus greater than Ba2 plus greater than Na plus. Yeah, that is very much correct. Because it is having 3 charges, this is having 2 charges and this is having 1 charge only. Okay. And what is the second statement? Coagulation power on a positive colloid. This is about negative on a negative colloid. Here it is on a positive colloid. The coagulation power. Here they haven't given ion, but the electrolyte itself is given. NaCl greater than Na2SO4 greater than Na3PO4. You have to remember here we are destroying or attempting to destroy or coagulate a positively charged colloid. So the negative ion or the anion will be the destroying agent or coagulating agent. Here which is the anion? Cl minus. Here it is sulfate ion. Here it is phosphate ion. Yeah. As per the statement, this must be the order. But we know the reverse is the order. So statement 2 is incorrect. So statement 1 is correct. Statement 2 is incorrect means first option, first choice is the correct answer. 1 is the answer for this question. Okay. Agreed, no? Now question number 56. This is also 2 statement type. We have to verify which all statements are correct and which is wrong, etc. Here the statement 1. The acidic strength of mono-substituted nitrophenol is higher than phenol because of electron withdrawing nitro group. Actually, it requires a correction in that statement. The acidic strength of mono-nitro-substituted phenol, not mono-substituted nitrophenol, but mono-nitro-substituted phenol, means one nitro group only. In a phenol, one nitro group is substituted. Such a phenol is more acidic than phenol itself. That is correct. We know whenever a nitro group is attached anywhere in the ring other than the OH group position in a phenol, it will be more acidic than phenol, correct, due to electron withdrawing nitro group. It is a correct statement. So, the nitrophenols are more acidic than the original phenol. It is a correct statement. Okay. Then what is the second statement saying? Orthonitrophenol, metonitrophenol and paranitrophenol will have same acidic strength as they have one nitro group attached to the phenolic ring. Now, about the position of this nitro group. The statement says that whether it is in the ortho position or meta position or in the para position, they will be equally strong because there is only one nitro group. We very well know that that statement is incorrect because the electronic effects operating from different positions in the benzene ring are different, leading to different acidic strength of nitrophenols, isn't it? We know that when the nitro group is in the para position, that nitrophenol, paranitrophenol, is the strongest phenol, isn't it? Then comes orthonitrophenol, last comes metonitrophenol. If you verify the pKa value, we know smaller the pKa value, stronger the acid, isn't it? See, pKa of simple phenol is 10. pKa of simple phenol is 10. Whereas paranitrophenol, it is 7.16. Orthonitrophenol, 7.24. Metanitrophenol, 8.39. This means paranitrophenol is the strongest. Then comes orthonitrophenol. Still then comes metanitrophenol. And last comes simple phenol. Why? See, in the case of orthonitrophenol and paranitrophenol, resonance can drain electron from this O. Lone pair of electron can be drained into the ring by resonance effect, isn't it? So what happens? It will become easier for hydrogen to be released as a proton. So in the case of orthonitrophenol as well as paranitrophenol, resonance effect is identical. So both are expected to be equally strong. But we know another effect operating is inductive effect, isn't it? So we may feel that since nitro group is closer to OH group here, orthonitrophenol should be more acidic than paranitrophenol because resonance effect is almost same. Then inductive drainage is more from the nearby position, but it is not so. There are several reasons. Among them, one is that there is a hydrogen bond, intramolecular hydrogen bonding possible between the hydrogen of the OH group and O of the nitro group. This makes it a bit difficult for orthonitrophenol to ionize. So, there is a slight decrease in the acidic character of orthonitrophenol due to the presence of nitro group in the ortho position due to hydrogen bonding. Okay. And there is one more reason we may expect. Since these two groups are at the nearest positions, there can be steric repulsion which may make these comets slightly out of ring, slightly. So, smooth resonance may be interrupted. So, even though there is resonance, but it may be slightly affected. For these two reasons, orthonitrophenol is not as much acidic as paranitrophenol. Coming to metanitrophenol, what happens? In the case of metanitrophenol, resonance brings an overall positive charge in the ring. But we know that positive charge never comes to the locant carbon carrying OH group. So, through resonance, electron cannot be drained into the ring from the OH group. Okay. So, of course, there will be an overall positive charge in the ring that may help metanitrophenol also to ionize a bit more easily than original phenol. but it is not as much as that of orthophenol and paraphenol. Got that? So we can conclude that paranitrophenol, strongest acid, then comes orthonitrophenol with some problems as we have already mentioned. Then comes metanitrophenol, where inductive effect helps. Then what also helps? Overall positive charge to the ring. Okay, that also helping here, making it more acidic than phenol. So paranitrophenol, then comes para, then comes ortho, then comes meta, then comes phenol. Okay, hope you understood that. So what we conclude in this problem, statement 1 is correct, that is any mono nitro substituted phenol, not mono substituted nitrophenol, mono nitro substituted phenol, mono nitro substituted phenol is acidic than phenol. That is correct. But the second statement that ortho, para and metanitrophenols are equally strong, that is a wrong statement. So here also statement 1 is correct, statement 2 is incorrect. Here also question number 56 is also getting 1 as the answer. Okay. Now question number 57. It is match the following type. You have list 1, list 2, and I have written on the board the result after matching. Okay, for to save time, etc. Okay. On the one side you have cyanohydrin, acetal, Schiff's base and oxide, and the other side you have HCN, alcohol, a primary amine and a hydroxyl amine. First list is products formed and list 2 reaction of carbonyl compound with. That is the meaning of the question. When a carbonyl compound react with the HCN, aldehyde or ketone react with the HCN or alcohol or RNH2 amine or hydroxylamine, the products are given here. This is the reactant that react with the aldehyde or ketone, and these are the products. So first given is product, second is the reactant. Okay. Now we have to match. It is from aldehyde ketone, you know that. The first one, cyanohydrin. We know when a carbonyl compound react with the hydrogen cyanide, first an addition product is formed, isn't it? What is that? O become OH and CN, the nucleophile get directly attached to the carbon. So this compound having both the cyano group and OH group is generally called a cyanohydrin. So we match A with the fourth option in the question paper. A matches with the 4 HCN. Now acetal. We know acetals or ketols or aldehydes are formed when a carbonyl compound, it can be either aldehyde or ketone, reacts with the alcohol. The reaction is carried out by passing dry HCl gas through a mixture of this carbonyl compound and alcohol. You pass dry HCl gas which catalyzes the reaction through a mixture of carbonyl compound and alcohol. 1 mole of carbonyl compound, listen carefully, 1 mole of carbonyl compound react with the 2 mole of alcohol in 2 stages, first forming a hemiacetal and then forming acetal. Look here, the carbonyl group, first react with the ROH group, then we have an addition product, H goes to this oxygen and OR goes to this carbon, then you have this compound, this carbon is having both the OR and OH. Okay. So it is called a hemiacetal. It is having an alcoholic group as well as an etheric group. Okay. It is an addition reaction. Now in the second stage what happened? This OH also get replaced by OR group. Second stage, all reaction is reversible. OH is also get reversed by OR group. So now it does not have alcoholic group anymore. it is having another OR group. So it is having two etheric linkages in the molecule, and such a compound is called acetal. So we come to conclude that we can clearly match acetal with the alcohol. Okay. Now, Schiff's base is obtained when a carbonyl compound reacts with a primary amine. It is a condensation product. Look here. The CO group condenses with the 2 hydrogen of the RNH2. So we have an imine, C double bond and R. Okay, such compounds belongs to the category imine, and this particular compound is called Schiff's base. Okay, so we can match Schiff's base with the primary amine. Okay, now last oxide. We match it with a hydroxyl amine, NH2OH, hydroxyl amine. Here also it is a condensation reaction. This O condenses with the 2 hydrogen and get removed. So we have C double bond NOH. Such a compound is called N-oxide. So our A, B, C, D respectively matches with the 4, 3, 2, 1, which is option 2 in the question paper. So our answer for question number 57 is 2. Okay. Now question number 58. It is another matching type question. We have on the left side ABCD, antacid, antihistamine, analgesic, antimicrobial. It is from chemistry in everyday life. On the other side, you have to match them against salvarsan, morphine, cimetidine, Seldate. It's all based on your memory power. Okay. If you remember, antacid that reduces the acid producing tendency of the stomach wall, isn't it? We know histamine is a biomolecule in our stomach which when attached to certain receptors in the stomach wall tend the stomach wall to produce more acid. So this biomolecule called histamine tend the stomach wall to produce more acid, leading to hyperacidity. And this medicine, cimetidine or Agamet, both are same. If we consume, it is an antagonist drug that competes with the natural histamine there and get attached to the stomach wall so that histamine cannot act upon the stomach wall. This reduces the tendency of the stomach wall to produce more acid. Okay, so this is a antagonist drug that which competes with the natural histamine and attached to the receptors where histamine should have been attached. It competes and first get attached so that histamine cannot do its role of producing more acid from the stomach wall. That reduces the hyperacidic condition. Okay. Now, antihistamine. See, histamine has many other roles. It is a vasodilator, etc., which controls the relaxation and the contraction of certain muscles, etc., in the gut wall, etc. See, when histamine has more other function, it produces allergic tendencies like sneezing, itching, etc. When we take certain medicine to moderate this tendency to sneeze, itching, etc., then only it is called antihistamine. Even though as an antacid also we take antihistamine, there it is not usually called antihistamine. Only when it is taken as a medicine to control this so-called itching, sneezing, etc., allergic responses, it is generally called antihistamines. There comes Seldane or terfenadine, both are same. There we use this antihistamine. You don't get confused. When some medicines are taken to lower the acidity in the stomach, it is not usually called an antihistamine. It is simply called antacid. Okay. Both are related to histamine. Please remember that. Now, third one, analgesic. That reduces pain, we know, in general. And we know morphine is a habit-forming or narcotic type analgesic. Morphine, codeine, heroin, etc. if you remember. So, analgesic matches with the morphine on the other side. And antimicrobial, salvarsan, discovered by Paul Ehrlich. It is an arsenic containing organic compound, something similar to a diazo group. AS, double bond AS group is there between two benzene ring, if you remember the structure. So, salvarsan is used as a medicine against a sexually transmitted disease, syphilis in male, isn't it? That medicine is salvarsan. It is used as an antimicrobial. Okay, bacterial, fungal, etc. infections. Okay, so this matching 3, 4, A, B, C, D versus 3, 4, 2, 1 comes in 4, option 4. So for this question, answer is 4. Okay. The next question, question number 59. Given below are half cell reactions. I have copied them on the board. MnO4 minus plus 8H plus 5E minus giving Mn2 plus 4H2O. That is here permanganate ion is getting reduced to manganese ion. As per this equation, permanganate ion is getting reduced to manganese ion. But see how they have given the half cell voltage E0, E standard Mn2 plus bar MnO4 minus. When a half cell is represented like this, it means Mn2 plus is the reactant and MnO4 minus is the product. This becoming this is the way of presentation. Okay. So here they have given not the SRP value but SOP value, that is oxidation potential, because Mn2 plus is getting oxidized to MnO4 minus where Mn is in plus 7, plus 2 becoming plus 7. That value is given as minus 1.510 in the question, isn't it? Minus 1.510. Okay. Then what it will, it's SRP, it's a opposite inside, 1.510. Okay. Let it be there. Now look at the second equation given in the question. Half O2 plus 2H plus 2E minus giving H2O. That is, oxygen is getting reduced to water. Oxygen, its oxidation state 0. Water, oxidation state of oxygen is minus 2. So 0 to minus 2 is reduction. So we can say oxygen it is getting reduced to water. And here how they have presented the voltage value, half cell voltage, E0, E standard O2 bar H2O. That is O2 becoming H2O. Okay, O2 becoming H2O. That is SRP value itself is given as 1.223. Okay. Okay. Now they have given two half cell reactions and now we know SRP values of both. When two such half cells are connected, what is the rule? That half cell with the higher SRP value has greater reduction tendency and will act as cathode, the other being the anode. That half cell with the higher SRP value is the cathode, the other being the anode. So here compare the two SRP values, 1.510, 1.223. 1.510 is the bigger value. So what happened? That will act as cathode, this will act as anode. Okay. So about the reaction which will happen, look here, this will act as cathode, isn't it? So the reaction happening here will be the forward reaction, isn't it? In the first case, since this acts as cathode, MnO4 minus become Mn2 plus. You got that? And what about the second one? Here it must act as the anode. Anode. What is the reaction in an anode? Oxidation. So H2O become O2. So when you, now we can say that here this is the reactant. Listen carefully. This is the reactant. Okay. And what is the product there? This is the product. In the net reaction, this will be the set of reactant and this will be the set of product, because here the reverse reaction is favored, oxidation is favored. So what you can say, MnO4 minus can oxidize water to oxygen. MnO4 minus can oxidize water to oxygen. And what will be the net cell voltage? That we know, SRP cathode minus SRP anode. Each standard cell is equal to SRP cathode minus SRP anode. 1.510 minus 1.223, giving you a positive SRP value. Okay. Now you look at the options. The question is like this. Will the permanganate ion MnO4 minus liberate O2 from water in the presence of an acid? Will such a reaction happen? We say yes. That is, permanganate can liberate oxygen from water. That tagged question is correct. It will happen. And the voltage will be plus 0.287. So, yes because E0 some other value given. No because E0 some other value given. Yes because E standard cell is 0.287. Last option, no because E standard value minus 0.287. We have to say yes because E standard cell is plus 0.287 volt. So our option becomes 3 for that question. Option 3 is the answer there. Okay. The 60th question. Here we have a set of hydrates given on the left hand side, and on the right hand side you have to match with the appropriate category of the hydride. Okay. The hydrates given are magnesium hydride, germanium hydride, boron hydride or diborane, and hydrogen fluoride. On the other side you have ionic, electron precise, electron rich, electron deficient. Now we categorize. See, we know magnesium hydride, even though is having some covalent character, is generally considered as an ionic hydride. So magnesium hydride is matched with the ionic hydride. Then germanium hydride, you have to remember carbon and germanium belongs to the same family. This is the carbon family member with a 4 covalent bond. So GeH4 is an electron precise hydride. Okay. Then B2H6, we know boron hydride or diborane involves 2 electron 3 center bond, isn't it? So it has to be considered as an electron deficient hydride. That's why 3 atoms have to share 2 electrons. That itself proves that it is an electron deficient compound. And finally we have hydrogen fluoride. We know in hydrogen fluoride around fluorine there is 1 bonded pair of electron and 3 lone pairs of electron. Whenever there are lone pairs of electron in the valence shell of the central atom, we call them electron rich, like ammonia, water and hydrogen fluoride. So that is cross matched with the electron rich hydride. Hydrogen fluoride is cross matched with the electron rich hydride. So this category, combination A4, B1, C2, D3. That combination is option 3. So our answer for this question, question number 60, is 3. Okay. Next question, question number 61. Here it is based on a buffer. In the question it is mentioned that a weak acid, acetic acid, is mixed with its salt, sodium acetate. Sodium acetate we know is a salt obtained from the weak acid, acetic acid and a strong base, sodium hydroxide. So it is a salt that fits into a buffer combination. So acetic acid, sodium acetate, they have mentioned the equal volume. 50 ml each of acetic acid and sodium acetate solutions are mixed. But acetic acid solutions initial concentration is 0.01 molar, whereas sodium acetate's initial concentration is 0.1 molar. So before finding the pH of the resulted solution, we have to find out the concentration of acetic acid and sodium acetate in the mixed solution, in the buffer mixture. Since equal volumes are mixed, initial concentrations of acetic acid as well as sodium acetate becomes half of the initial concentration, isn't it? When equal volumes are mixed, concentrations will be halved. In the case of both acetic acid and sodium acetate, it is easy to guess, but I have shown them mathematically also. Concentration of salt after mixing, M1V1 is equal to M2V2. Initial concentration of salt, sodium acetate is 0.1. Its initial volume is 50 ml. Final concentration we want to know. Present volume is 50 plus 50, 100 ml. So M2 is equal to 0.05. Likewise, we have to find the acid concentration in the buffer after mixing. M1V1 is the same. M1V1 is equal to M2V2. Initial concentration of acid is 0.01. 0.01 into 50 is equal to M2 into, after mixing it becomes 100. So into 100. Then M2 is equal to 0.005. It is 0.05. Here it is 0.005. Now we apply Henderson's buffer equation for acid buffer. pH is equal to pKa plus log concentration of salt by concentration of the acid in the mixed solution. pH is equal to pKa, acid constant for weak acids, plus log concentration of the salt by concentration of the acid after mixing. Okay, pH is equal to the pKa values given in the question, 4.75, plus log salt concentration 0.05, acid concentration after mixing 0.005. This gives you 10. So 4.75 plus log 10. Log 10 is 1. So 4.75 plus 1, 5.75. The third one is the answer. 3 is the answer. 5.75 is the answer. It's a good question. Okay. Now we go on to question number 62. It is from solid state based on defects in the crystal. It is assertion reason type, similar to statement 1, statement 2 type. Okay, we will read the assertion first. In a particular point defect, an ionic solid is electrically neutral, even if few of its cations are missing from its unit cells. See, there are two physical defects we come across. They are Schottky defect and Frenkel defect. In Schottky defect, both the cation and anion are missing from the unit cell, not cation alone. In Frenkel defect, cations are just dislocated from their original position to interstitial spaces. Just dislocation type. Schottky defect is a missing type, whereas Frenkel defect is a dislocation type. And you have to remember that these interstitial vacancies are also a part of unit cell. Okay. This defect cannot be Schottky defect. Why? Because in the statement they haven't mentioned anions are also missing from the unit cell. So since only cations are mentioned to be missing, it cannot be Schottky defect. Can it be Frenkel defect? No. Why? Because they are saying that cations are missing from the unit cell. Interstitial positions are also a part of the unit cell. So, if they are dislocated, they will be still remaining within the unit cell. But they have mentioned they are lost from the unit cells, means they have lost from the crystal. So, it cannot also be Frenkel defect. So, it is actually what they have mentioned here is an impossibility. So, assertion is wrong. Now read the second statement. Reason. In an ionic solid, Frenkel defect arises due to dislocation of cation from its lattice site to interstitial site, maintaining overall electrical neutrality. That is the exact statement for Frenkel defect. What they have mentioned is clearly correct, isn't it? In Frenkel defect, cations are dislocated to interstitial lattice positions. Interstitial lattice positions are also a part of the unit cell, because unit cell is the representative part of the crystal, which also include interstitial positions. So, that statement is correct. So, we have concluded that assertion is wrong, reason is correct. Okay, assertion is wrong, reason is correct. So, our option is A is not correct, R is correct. Option 2 is the answer. Option 2 is the answer. Okay. So question number 62 has the answer 2. Next question, question number 63. It is related to enzyme activity. It has some connection with the surface chemistry where we discuss catalytic activities. It has some connection to kinetics also because it's related to speed of the reaction. Okay. The question is like this. The incorrect statement regarding enzyme is 4 options. First one, enzymes are polysaccharides. We know enzymes are polyamides or protein molecules. So it is incorrect to say enzymes are polysaccharides. So the very first statement is incorrect. Second option, enzymes are very specific for a particular reaction and substrate. Yeah, it is very much true. An enzyme that catalyzes one biochemical process cannot catalyze another. So this statement that enzyme react activities are highly specific is very much correct. Second statement is correct. Third one, enzymes are biocatalysts. Evidently, enzymes are biocatalysts. And the last statement, like chemical catalyst, enzymes reduces the activation energy for bioprocesses. What's the role of a catalyst? When reactants become products, the reactants first get converted to an activated complex having a high energy, which later breaks down either to the products or back to reactants. Okay. So, first they must get converted to an activated complex by absorbing certain amount of energy. For example, if the reactants are A2 and B2, A2 and B2 must absorb a specific amount of energy and get converted to the activated complex A2B2 star, which later breaks down to product 2AB, okay, or back to A2 and B2. Okay, suppose you are using a catalyst. The catalyst, in the presence of catalyst, the reaction adopts a new mechanism or new path of reaction, or it involves a new activated complex of low activation energy requirement, say, let's call it A2B2C star. C, A2 plus B2 plus, if you are using catalyst, we have a new activated complex A2B2C star whose required activation energy is less, and the product, while it becomes the product 2AB, catalyst is regenerated plus C. Okay, so we see that in the presence of a catalyst, the activation energy is less or the energy barrier to be crossed so that reactant become product is low in height. Energy barrier is lower in energy requirement. So the conversion becomes easy. Okay. So this statement that like chemical catalyst enzymes reduces the activation energy of the bioprocess is very much correct. So our answer, we stick on to answer 1. Okay. Now the question 64. It is from S block elements, alkali metals. Identify the incorrect statement from the following. Ionization enthalpy of alkali metals decreases from top to bottom in a group. Yeah, it is very much correct. Ionization enthalpy of alkali metals decrease down the group because down the group atomic sizes increases. So nuclear attraction experienced by the valence electron decreases. Ionization become more easy, or you have to expend less energy to ionize an isolated atom in the gaseous state. So ionization enthalpy as per definition decrease down the group. That is correct. Lithium is the strongest reducing agent among the alkali metals. They didn't mention whether the reaction is happening in gaseous state or in aqueous solution or in solid state, etc. If it is in gaseous state, lithium has the highest ionization enthalpy, and so will be the weakest reducing agent. If it is in aqueous solution, other option, let's keep aside solid state. If it is in aqueous solution, we know that here also ionization enthalpy required is the same. But immediately after that, the lithium ion formed is heavily hydrated, isn't it? Heavily hydrated, and so a large quantity of hydration energy is liberated. This is much high compared to the bigger cations like sodium, potassium, rubidium, cesium, etc. So very high quantity of hydration enthalpy is absorbed, released, which more than compensate its high ionization enthalpy requirement. So what happens is that the net effect will be release of energy than absorption of energy. So maximum energy is released when lithium acts as a reducing agent in aqueous medium, not sodium, potassium, rubidium, cesium or francium. This makes lithium the strongest reducing agent in aqueous medium. When compared to gaseous state, the trend is reverse for lithium, the other way about lithium, due to the large quantity of hydration enthalpy released. Okay, but that advantage is only for lithium. For others, the order of reducing power is same whether it is in gaseous state or in aqueous medium. So the strongest reducing is lithium. Then comes francium, cesium, rubidium, potassium and sodium. So in aqueous medium, weakest is sodium. The next, lithium is the strongest reducing agent. Next member, sodium is the weakest reducing agent. So the advantage of being small atom and heavy hydration enthalpy is only valid for lithium ion. So lithium ion is the strongest reducing agent in aqueous medium. Mostly they mean this reducing power in aqueous medium. Let's keep it pending for the time being because option 2. Now coming to 3. Alkali metals react with the water to form their hydroxide. Yeah, we know. Lithium becomes lithium hydroxide, sodium becomes sodium hydroxide, etc. Okay, that's correct. The oxidation number of K in KO2 is plus 4. See, usually we calculate, if we compare this with the CO2, we may go wrong because in carbon dioxide, carbon's oxidation state is plus 4 because carbon dioxide is a normal oxide. Normal oxide means oxygen is in the oxidation state minus 2. So in carbon dioxide, we know carbon is, both oxygens are taken to be minus 2. So carbon has to be plus 4. But here the situation is different. It is an ionic compound. And here the oxide is not normal oxide but a superoxide with a 1 minus charge per O2 unit, O2 molecule. So here also potassium remains unique positive. It is a superoxide. That's why the oxidation state of potassium remains plus 1. So this statement is definitely wrong. So if you compare 2 and 4, we must opt 4 as the answer, not a 2. Because at least in aqueous medium, it is the strongest reducing agent. Even though in gaseous medium, it is the weakest. Okay, so we choose the answer 4. Okay. The 65th question, it is about diborane. So from plus 1 chapter P block element, it is boron family, diborane compound, diborane. It is regarding the structure of diborane. See, if we draw B2H6 like C2H6, the structure would have been like this. Tetrahedral, both boron, sp3 and this tetrahedral structure would be similar to this. But this structure requires 2, 4, 6, 10, 12, 2, 4, 6, 8, 10, 12, 14 valence electron for B2H6. But we know boron is having only 3 valence electron. Every hydrogen is having 1 valence electron. Then if we add 3 plus 3, 6 plus 6 hydrogen, only 12 valence electron, not 14 valence electron. So a structure similar to ethane is not possible for diborane. Then on further detailed study and analysis, a scientist called Willard Lipscomb suggested a peculiar structure for diborane, for which he was awarded Nobel Prize. The structure involved 2 3-center 2-electron bonds. Not 2-center 3-electron bond, but a 3-center 2-electron bond. Look here. Here in this particular structure, both boron atoms are sp3 hybridized. sp3, and so around each boron 4 bonds are arranged tetrahedrally. So look at this diagram down here. In this diagram, I have drawn the molecule like this. Two hydrogen on both sides are perpendicular to the plane of the board, like this on this end and like this on the other end. But at the central part it is like this and this. So this central part is on the plane of the board, but the terminal parts are perpendicular to the plane of the board. Okay. Both the boron are sp3 hybridized, and see, this is the 3-center 2-electron bond. We know each boron is having only 3 valence electrons. So look at this boron. 1 valence electron is used here, the second valence electron is used here, and the third valence electron is present here. It has only 3 valence electrons. Look at this boron. 1 valence electron here, the second valence electron here, the third is here. So if one valence electron is involved in this bond, the other boron's 1 valence electron is involved in this bond. Hydrogen also can contribute 1 valence electron. Here also hydrogen contribute 1 valence electron. So these are the 2 3-center 2-electron bond, which are called the banana bonds or bridging bonds. 3-center 2-electron bonds. So this is the structure of the diborane. You have to remember, this plane and this plane will be the same. If you draw it, imagine it as a continuation. This hydrogen, this boron, this hydrogen remains in one plane. At the same time, you can also say this boron, this hydrogen, this boron, this hydrogen remain in a perpendicular plane. Boron is common in both planes. Okay. Hope you understood this. Now we will verify the options given. First option. The 4 terminal hydrogen atoms and the 2 boron atoms lie in one plane. Correct. This hydrogen, this boron, this hydrogen lie in the same plane of the plane. Same plane in space. Correct. Boron and boron atoms are sp2 hybridized. No, it is not. It is sp3 hybridized with the tetrahedral disposition of 4 bonds around it. So statement 2 is incorrect. 2 must be wrong. Well, there are 2 3-center 2-electron bonds. Correct. Okay. And lastly, the 4 terminal pH bonds are 2-center 2-electron bonds. Yeah, correct. 2-center 2-electron bond means normal covalent bond. 2-center 2-electron, it is correct. Only the bridging bonds are 3-center 2-electron bond. So our answer remains to be option 2. Okay. Now we have the 66th question. It is from gaseous state, states of matter, chapter. Which one is not correct mathematical equation for the Dalton's law of partial pressure? Here P is the pressure of the gaseous mixture. P is the total pressure of the gaseous mixture. And Pi used here is the pressure of the ith gas. If there are 1, 2, 3, etc. gases, every gas, generally any gas is represented as Pi, and its mole fraction is Chi I. Chi I and Pi are the general representation for P1, P2, P3 and Chi 1, Chi 2, Chi 3. Remember that. We know that from the gaseous laws, we know that partial pressure of any gas is total pressure into mole fraction. We know that partial pressure of any gas is the product of total pressure into mole fraction. Okay. Now the first equation. We have to verify which is the correct equation. They have given in sentence. I have written on the equations here. Pi is equal to Chi I into P. That is partial pressure of any gas is total pressure into mole fraction of that gas. It is correct. Second one. Pi is Chi I into P0. Both of these cannot be correct. Since this is correct, this must be wrong. Isn't it? Okay. And we will verify it. Partial pressure of one gas is partial pressure of that gas when it is pure into mole fraction. How that can be correct? When that gas alone occupies the total volume occupied by the gaseous mixture, that itself is called partial pressure. So what happened here? PI and P0 are equal. See, what is partial pressure? Partial pressure of a gas in a mixture of gases is the pressure exerted by that gas alone if it alone occupies the whole volume occupied by the gaseous mixture. That itself is the partial pressure. Okay, so P0 is nothing but PI. So I become 1, isn't it? So this equation is very much wrong. Here it has to be, total pressure has to be used and not the pressure of the individual gas, because in individual gas pressure is called partial pressure. Means PI and P0 or P standard is the same here. So this equation is very much wrong. Now third one. P is equal to P1 plus P2 plus P3. That itself is the mathematical statement for Dalton's law of partial pressure. In a gaseous mixture, the total pressure occupied by all the gases together is the sum of partial pressures of the individual gases, isn't it? So this equation is nothing but the mathematical expression for Dalton's law of partial pressures. And lastly, they have given P is equal to N1 RT by V plus N2 RT by V, N3 RT by V. Is that correct? We know that total pressure is sum of partial pressures. Now each gas can be separately considered as to be ideal with the equation PV is equal to nRT. Okay. So P1 will be N1 RT by V, P2 will be N2 RT by V, P3 is equal to N3 RT by V. Here we need not write V1, V2, V3 because the whole volume is available for all gases all the time. Volume is not shared. It is enjoyed by all gases equally. So we shouldn't write V1, V2, V3. V is a common term for that. So this equation is also valid. So we come to the conclusion that for this question number 66, answer is 2. Okay, right. Next question, question number 67. It is from coordination complexes and connected to naming of complexes. Okay. See, before entering into the question, I have to tell you something. There are certain metal atoms whose name is mentioned differently when it becomes a part of cation and when it becomes part of anion. Some common examples are given here. For example, see metal iron. Its Latin name is ferrum. Okay. When it is present as a part of cation, the name iron is used. But when it is part of anion, it is ferrate from the name ferrum. So here it is iron, here it is ferrate. Okay. That difference is there. Again, coming to the case of tin, Sn, from the name stannum. When it is part of cation, tin is used. Okay. But when it is part of anion, it is not tinnate, but a stannate. Okay. Third case, lead, Pb, from plumbum. When it is part of cation, we simply use lead. But when it is part of anion, instead of leadite, we use plumbate. Copper, Cu, from the name cuprum. When it is part of cation, normal name copper. But when it is part of the anion, it is cuprate. Okay. Now, next silver, Ag from argentum. When it is part of cation, it is silver, not argentum. But when it is a part of the anion, it is argentate. Okay. Next, gold, aurum. When it is part of cation, it is gold. But when it is part of anion, we use the term aurate. Okay. Keep that in mind. Now, look at this complex. AgH2O twice, AgCN twice. Okay. We know water is a neutral ligand, whereas cyanide is a ligand with a 1- charge. So, we know silver in most of its compound exists in +1 state. So, since this H2O is neutral, its total charge will be +1. And here, again silver +1, each cyanide -1. So, resultant charge will be -1. So, this is the structure of the molecule. Now, we name it diaqua silver Roman 1 because it is +1 Roman 1. A little space between cation's name and anion's name. Dicyanido argentate again 1. Both are 1, isn't it? Diaqua silver 1, dicyanido argentate 1, and this corresponds to the option 2. So for question number 67, option is 2. Now we have the 68th question. We can say this question is either from chemical bonding or P block elements second year, because here we discuss the structures of some P block elements of the higher groups. P block elements of the higher groups. Okay. See, what is the question? Amongst the following, which one will have maximum lone pair repulsion, electron pair repulsion? And the given options are SO4, XCF2, ClF3, IF5, for which we have to know the structure. First we will consider SO4. Sulfur atom in its ground state has only 2 unpaired electrons. But here we want 4 unpaired electrons because we require 4 bonds. So one pair gets excited to vacant d orbital. So now it has 1 lone pair, 4 unpaired electrons. These 4 unpaired electrons can form 4 bonds. So now it undergoes sp3d hybridization. Remember, here 1 is lone pair, whereas the remaining 4 will become bond pairs after bonding with the fluorine atom. So how nature arranged them? According to VS EPR theory, for maximum stability, they get arranged this way. That is, 2 fluorine sulfur bonds are axial, remaining 2 fluorine sulfur bonds are equatorial, and 1 lone pair is also in the equatorial position. So electron pair geometry or structure is distorted trigonal bipyramidal. Electron pair geometry or structure is distorted trigonal bipyramidal. Whereas molecular geometry or shape, which excludes lone pair, is seesaw shape. Seesaw shape. Okay. But here there is only 1 lone pair. So there is no question of lone pair electron repulsion. So that's it. Now we go to the second case, XCF2, xenon difluoride. Xenon in its ground state has no unpaired electron. Here we want to form, the molecule want to form 2 bonds. So 2 unpaired electrons. So 1 electron get excited. So it undergo again sp3d hybridization. Here there are 3 lone pair, 2 bond pair. And as nature arranged them, which is explained by VSEPR theory as this. That is, 2 bonds axial, 2 XCF bonds axial, 3 lone pairs equatorial. That's the way they arrange. So electron pair geometry or structure is which considers all lone pairs, all electron pairs in the valence shell. Then it is called structure or electron pair geometry is trigonal bipyramidal. But shape or molecular geometry which excludes lone pair linear. Okay. Now here there are more than 1 lone pair and the angle between any 2 lone pair is 120 degree. Let it be there. We have to compare with others. The next case, ClF3. Chlorine has only 1 unpaired electron, but here 3 covalent bonds to be formed. So 1 pair metal gets excited. So it has 2 lone pair and 3 lone electron which will become later bond pairs after bonding with the fluorine. So here also it is sp3d hybridization, 2 lone pair, 3 bond pairs, and how nature arranges them for minimum repulsion and maximum stability. It is this way. 2 CLF bonds are axial, remaining CLF bonds are equatorial, 2 lone pairs are also equatorial. That's the way the molecule gets arranged. Okay. Here also there are 2 lone pairs of electron. Both are equatorial. What about the angle? Its angle we will discuss later. Next case, IF5, iodine pentafluoride. Iodine also belongs to chlorine, so electron arrangement will be similar. There is only 1 unpaired electron now. It wants 4 more unpaired electrons to form 5 bonds. So 2 pairs get excited. So 2 electrons get promoted to d orbital. Then it undergoes sp3d hybridization, d2 hybridization. I'm sorry. Now there is 1 lone pair. All the remaining are bond pairs, isn't it? That is 1 lone pair and 6 bond pair. For sp3d2 hybridization, the electron pair geometry or structure is octahedral. We know. Octahedral, we know. and it's a molecular geometry or shape. See here 5 are normal bonds. The 6th is a lone pair, isn't it? So that lone pair can be drawn on any line because all the 6 positions are identical in octahedral structure. But for convenience, we usually show it downwards. Okay, even though all positions are identical in diagram, it is mostly shown downwards. So what about its structure? Its structure is somewhat distorted octahedral. Electron pair geometry structure is somewhat distorted octahedral. What about the shape? You have to exclude the lone pair. Shape is molecular geometry, excluding lone pair. It is square pyramidal. Square pyramidal. Here also there is only one lone pair electron. So there is no question of lone pair repulsion here also. Now the option is between these two. We have to choose from these two. See, here there are 3 lone pairs of electron mutually repelling. So if net repulsion will be more here. Here there are only 2 lone pairs, so net repulsion will be less. Here all the angle will be 120. But here, since this bond is this is bond pair of electron, lone pair bond pair repulsion will be less, and the lone pair in the equatorial positions, lone pair repulsion will be more, and the lone pair bond pair repulsion will be less. So what happens? These 2 lone pairs get more distanced from one another. They get moving away from. So here the bond angle will be more than 120. Here they will be exactly 120. All the bond angles. So our answer for maximum bond angle, lone pair repulsion will have maximum lone pair electron repulsion. Maximum lone pair electron repulsion will be here. But if they were asking bond angle, it will be here. So maximum bond angle, maximum repulsion will be in the option 2. Okay. So 2 will be the answer here. Okay. Question number 69. This is from hydrocarbon aromaticity. Okay. First year. Question number 69. Which compound amongst the following is not an aromatic compound? Okay. Actually, they should have used the species because there is only one compound. Others are part of a compound or ions only. Okay. Which species is aromatic? You know the condition for, basic condition for aromaticity. There must be 4n+2 circularly delocalized pi electron. Cyclically delocalized pi electron 4n+2 where n is 1, 2, 3, 4 etc. So that there must be 2, 6, 10, 4n+2 numbers, etc. circularly delocalized pi electron for aromaticity as per Huckel's rule. Okay. Look at the first case. There is only 2 pi electron. But here there is a positive charge. See, so delocalization is possible. How? This bond later becomes a bond here, so that positive charge shifts to this position, as in this case. Again, this bond shifts to this position, so that positive charge shifts to that position, like that. So, in a way, electron pair can keep on moving within the, it is like this, becoming like this, then becoming like this, then becoming like this, then there. So, it changes like that. Okay. So, circular delocalization of 2 pi electrons are involved there. So, that species is aromatic. It is cyclopropenyl carbocation. It is aromatic. This is 1,3,5-cycloheptatriene. Is it here? There are 6 pi electrons, but it is not cyclically delocalized because this carbon, without any vacant orbital for these electrons to move around, that prevents, this carbon prevents cyclic delocalization. So it is not aromatic. Of course, resonance can happen this way. It can oscillate. Resonance can be delocalization this way. And so it is not aromatic, but resonance is there, but it is not cyclic. So it is called, it comes under the category non-aromatic. Not anti-aromatic, non-aromatic. It is not aromatic, it is non-aromatic. Now the third case, cyclopentadienyl carbanion. Here it is negative charge. So what is the total number of electrons here that can be delocalized? 2 from this, 2 from this. This negative charge should be considered as 2 electron, not 1 electron. Why? This carbon has its own electron that does not provide it any charge. And one more electron that it obtained from another atom. That's why it is shown by negative charge. So that negative charge does not correspond to 1 electron but 2 electron. Okay. So as a whole there are 2, 4, 6 electrons. Okay. 6 electrons. Can they cyclically delocalize? Of course. This lone pair can become manifest as a double bond here. Then this bond pair reduces to this corner like this. And this will continue again. This negative charge spreads as a bond here. Then this bond reduces to a negative charge into this corner. It becomes this. And it may continue like that. So there is cyclic delocalization of 4n plus 2, 6 pi electron. So cyclopentadienyl carbanion is aromatic. What about this? It's a carbocation. Cycloheptadienyl carbocation. In your text it is called a tropylium ion. Yeah. Here, since now this has a vacant orbital for the circular delocalization of this 6 pi electrons, it is aromatic. See how it delocalized? This double bond comes over here, as in here. So the plus charge reaches this corner. Then this lone pair moves over, this pi bond moves over here. So positive charge reaches here, as in this. So there is also cyclic delocalization of pi electrons. So, and that too 6 pi electron again. So this is also aromatic. So our answer will be 2. 2 is our answer for question number 69, which is non-aromatic, not anti-aromatic. Now, question number 70, statement 1, statement 2 type. Given below 2 statements. Statement 1, the boiling points of following hydrates of group 16 elements increases in the order H2O less than H2S less than H2SE less than H2PE. Statement 2. The boiling points of these hydrates increases with the increase in molar mass. We will check. See, this is the given order of boiling point. But if you have studied, the actual order of boiling point is like this. H2S, H2SC, H2TE. That is correct. This part is correct. But H2O, due to its extensive intermolecular hydrogen bonding, has the highest boiling point here. And its boiling point we know 373 Kelvin. So that takes an unexpected position there. So now we are sure that statement 1 is incorrect. What about statement 2? The boiling points of these hydrates increase with the increase in molecular masses. As far as this part is considered, that statement is true. But if we include this, that statement goes wrong. And the point here is that it includes this also. So we have to consider that both statements are incorrect. Okay? And I opted both statements incorrect for. If at all they choose option 2, statement 1 is incorrect, but statement 2 is correct, that is this statement 2. The boiling points of these hydrates increase in the increase. There's least possibility for that. Because in these hydrates they mention. There, this becomes an exception. So, there is hardly any chance that 2 is opted as an answer. If at all they opted 2 as an answer, you have every right to question that option. Okay? We will proceed to the next. Question number 71 is a so simple question. In 1 molar solution that contains 0.5 mole of a solute, there is 1000 ml solvent, 1000 gram solvent, 500 ml solvent, 500 gram solvent. We know as per definition, 1 molar solution we get when 1 mole of solute is present in 1000 gram of solvent, not 1000 ml of solvent, isn't it? 1 mole solute when present in 1 kilogram solvent or 1000 gram solvent, we have 1 molar solution. So if you are taking only 0.5 mole solute, half of this, denominator must also get halved, 500 gram of solvent. Then only it remains to be 1 molar solution. So when it is 0.5 mole solute, you have to take 500 gram of solvent, isn't it? So our option for this is 4. 4 is the answer for question number 71. Okay, very simple. Now question number 72. It is regarding the stability of diazonium salts. So it is a question from amines of second year. What are the statement? First statement. Primary aliphatic amines react with the HNO2, nitrous acid, to give unstable diazonium salt. That's a correct statement. We know primary aliphatic amine reacts with the nitrous acid HNO2. We know nitrous acid itself is an unstable acid, and so it has to be prepared on the spot in situ in the reaction mixture by mixing dilute solution of sodium nitrite and dilute solution of hydrochloric acid in the temperature range 0 to 5 degrees Celsius. Then it forms nitrous acid HNO2 and NaCl, of course NaCl. So, but as soon as that HNO2 is formed, it reacts with the aliphatic primary amine to produce alkyl diazonium chloride, which is highly unstable, and even at this low temperature, it is hydrolyzed by water to produce a primary alcohol plus nitrogen gas which is evolved and HCl. So this first statement is correct. That is statement 1. Primary aliphatic amines react with HNO2 to give unstable diazonium salt is correct. What about the second statement? Statement 2. Primary aromatic amines react with HNO2 to form diazonium salts which are stable even above 300 Kelvin. See, we say compared to aliphatic diazonium salts, aromatic diazonium salts are more stable. Up to in the room temperature range. Even then, we may say it is stable up to 25 degrees Celsius or 298 Kelvin. Above that temperature, even this become unstable. Okay, even this become unstable, and their stability is mainly in aqueous solution only. In the dry solid state, even in this room temperature, it tend to decompose. Of course, there are exceptions like benzene diazonium fluoroborate. That's a case of exception only. Generally, they are unstable above room temperature. So the second statement it cannot be accepted because they are saying that they are stable even above 300 Kelvin. So we have to accept that as the incorrect statement. So why it is stable? Why aliphatic diazonium salts are unstable whereas aromatic diazonium salts are stable? Probably because of this resonance stabilization. Look at this resonance change. This pair of electrons in the benzene ring can resonate over here as a double bond. At the same time, this pair of bond moves on to the nitrogen. So what happened? This nitrogen continues to remain plus charge because on one side it gets a new bond, on the other side it loses one existing bond. So this N remains N plus. This becomes N minus because now around this nitrogen atom there are 6 valence electrons. 1, 2, 3, 4, 5, 6. Whereas originally it was only 5 valence electrons. That's why it is gaining 1 minus charge. What about this nitrogen? It has right now it has only 4 valence electrons around it. It has lost 1 electron. That's why it is positive charge. We know this carbon now acquires a positive charge. That positive charge can continue to resonate within this ring. It may come over here, then it may go over here. Okay, so probably because of this resonance is not much stable, much favorable because it is having 2, 3 charges in the same molecule. Still it is happening to some extent. That may be a cause that this is a bit more stable than aliphatic primary amine. But even above 300, even in this case, above 300 Kelvin, they tend to decompose. Okay. So we take that statement 1 is correct, but statement 2 is incorrect. That is option 1 can be chosen as the answer. Option 1 can be chosen as the answer here. mostly. Next question is question number 73. It is regarding gadolinium atom. It is from D block, D and F block elements. The question is, gadolinium has a low value of third ionization enthalpy because. So this question is with respect to a lanthanide element, gadolinium, and you can answer this question only if you know the atomic number as well as electronic configuration of gadolinium. Gadolinium is the 64th element with the valence configuration xenon, xenon's configuration plus 4s7, 5d1, 6s2. Okay. See here, when it loses the first two electrons, these two electrons will be lost, and the GD2 plus will be Xc4s7, 5d1. And when it loses the third electron, GD3 plus, this d electron is lost and 4s7. What is the advantage of having a configuration like 4s7 in the valence shell? See, it is an exactly half-filled state for F subshell. See, when the electrons are electrons within a subshells, which are identical in energy as well as in spin, can undergo mutual exchanges within the subshell as well as among identical subshells. How they mutually exchange their position within the subshell? For example, this electron can exchange with any of the remaining 6 electrons mutually. So for this electron there are 6 possible mutual exchanges. For this electron the remaining 5 exchanges possible. For the next 4, then 3, then 2, for this 1, this is nil. So there are altogether 6 plus 5 plus 4 plus 3 plus 2 plus 1, or 7 into 6 by 2. This is 21 intrasubshell exchanges between electrons. Now if we consider suppose we consider only 2 subshell, how many intersubshell electron exchanges between identical electrons is possible? This 7 electron can exchange with any of these 7 electrons. So total number of possible exchanges between any 2 subshell will be 7 into 7, 49 exchanges possible, intersubshell exchange. So the total number of exchanges, if you consider only 2 subshell, 21 plus 49, 70. There are large number of subshells and large number of possibility of such a intersubshell exchange, etc. So greater the number of electron exchanges like this, greater the delocalization effect of the electron, greater the delocalization, lower the potential energy of the system as a whole. So there is a lowering of energy due to such kind of electron exchanges, lowering of potential energy due to such exchanges, and this lowered energy is called exchange energy. So higher the magnitude of exchange energy, more stable the atom is. Okay, more stable the metal electronic configuration. So we can say that 4f7 has this advantage. But you may have a doubt. Even this is having such an electronic configuration, even the presence of this. Our answer is that whether this electron is present or not does not add too much advantage to the atom in stability. So losing that electron is not much a big problem for that regarding the stability. So it is not very difficult to ionize that electron. That's why even though both are having this electronic configuration, this is, I don't say better stability. Losing this electron does not cause any problem to this metal electronic configuration. So it easily loses the third electron. That's why gadolinium 2 plus easily become gadolinium 3 plus. Okay, hope you understood. Question number 74. You can say it is from halo alkanes and haloarine. Which of the following is suitable to synthesize chlorobenzene is the question. Which will give you chlorobenzene as the main product. The first reaction they have mentioned is benzene and HCl. There is no known or popular reaction between benzene and HCl. Okay, so no reaction. Then aniline and HCl. Aniline is a base and HCl is an acid. Upon heating, they may be forming a salt, anilinium, benzene, Anilinium hydrochloride. Anilinium hydrochloride. Okay. That's the only possibility. Now chlorobenzene. And the third one, benzene plus chlorine in the presence of anhydrous ferric chloride. That's a popular method for preparing chlorobenzene. Actually, it requires darkness to avoid any photochemical addition of chlorine across the double bond in the aromatic ring. Actually, darkness is also recommended. Then what happens? We get a Cl2, so one chlorine substitute, one of the hydrogen giving you chlorobenzene in HCl. It happens in the presence of ferric chloride because ferric chloride produces chloronium ion, FeCl3 plus Cl2, in FeCl4 minus Cl plus. This Cl plus, which is an electrophile, attracts the electron-rich benzene ring to form an intermediate. A benzene carbonium intermediate also carrying a chlorine atom, which later eliminates one proton, which this proton reacts with the AlCl4 minus or FeCl4 minus. I'm sorry, if you are using FeCl4, it will react with the FeCl4, giving you what? Chlorobenzene, ferric chloride, which is regenerated, and HCl as the side product. So, this is a familiar method for producing chlorobenzene. We have studied that. And lastly, phenol plus sodium nitrate plus HCl. It is only aniline that reacts with a mixture of sodium nitrate and HCl producing benzene diazonium chloride. Phenol is an acid. The HNO2 produced from NaNO2 and HCl is another acid. So there is no possibility of any reaction between these two. Okay. So no product. So there is no further reaction with the CuCl. There is no question of Sand-Meyer's reaction there. So you cannot prepare chlorobenzene by that method. So our answer comes out to be 3 for question number 74. Okay. The next question 75. It is a reaction of a Grignard reagent. Grignard reagent are alkyl or aryl magnesium halide. And this reaction studied here is to produce carboxylic acid. So we can say this question is either from haloalkane and haloalene or from aldehyde ketone and carboxylic acid. It can be included in both chapters. Okay. What's the reaction between Grignard? The question is RMgX plus CO2 in dry ether gives you an intermediate product Y, which upon acidic hydrolysis gives you a carboxylic acid RCOH. Then what is Y? What is that intermediate product? That's the question. See, we have learned that Grignard's reagent RMgS can react with a dry carbon dioxide. Dry carbon dioxide or dry ice. Not dry carbon dioxide, solid carbon dioxide, which is called a dry ice in either medium. What's the reaction? This R is having a partial negative charge, so it can act as a nucleophile and it attacks this carbon. At the same instant, this oxygen withdraws this electron towards itself, so it becomes O minus, and now it acts as another nucleophile and attack NGX. A mutual attack, mutual nucleophilic attack. R attack C, due to that a secondary attack, O attack NGX. So what we get? We get R C double bond O. One C double bond O remain as such, and the other become OMGX. RCO OMGX. This is Y. This is the intermediate. This upon acidic hydrolysis gives you carboxylic acid, isn't it? Carboxylic acid and MgXOH. Side product is not very much important here. Okay, we get that side product. This can be written like this: RCOO minus MgX plus. That plus charge resides on magnesium since it is a metal. So among the given options, third option suggesting RCOO minus Mg plus X will be our answer for question number 75. 3 is our answer. Question number 76. See, it is regarding the shapes of different d orbitals. So you can say this is a question from atomic structure first year. Okay. First I will briefly mention the shapes of 5 d orbitals. D orbitals are arranged around the 3 coordinate axes x, y and z. In all these diagrams, we have maintained x and y in a plane perpendicular to the board and the z-axis in perpendicular direction. Okay. So we have dxy, dyz, dxz orbital, then dx square minus y square and dz square orbital. dxy, dyz, dxz has the speciality that their lobes come in between the axes. For instance, dxy comes in between, its lobes comes in between x and y axis, dyz in between y and z axis, dxz come in between x and z axis. First thing. So they are called the non-axial orbitals. See, look at the dxy orbital, x-axis, y-axis, z-axis. No? So when you draw a dxy orbital, you can ignore the z-axis and focus on x-axis and y-axis, which is existing like this in the diagram. Now when you draw the dxy orbital, for visual effect, you have to fill the angle like this. This obtuse angle, you fill it like this. Then this acute angle, this. Then these two are away from the observer. So make them small but keep filling. So that you get a visual experience. You are seeing a orbital placed in a pair of axes like this. That is dxy. Now, while you draw dyz, you bother only about y-axis and z-axis. Ignore x-axis. And these two axes are staying like this, perpendicular to the plane of the board. Again, this was also perpendicular to the plane of the board. This is also perpendicular to the plane of the board. A third different plane. See, here these two lobes are towards you, these two lobes are away from you, isn't it? You are bothering only about y and z axis. So these two has to be drawn bigger, these two smaller. Then you get the visual experience. Now dxz. X-axis and z-axis are on the board's plane. So the lobes will also remain on the plane of the board. They will be appearing at equal distance from the observer. Say they will have the same size. All are in between the axes. dxy, xz. Okay. Now, the remaining two are, they are called non-axial orbital and in spectroscopically they are designated as T2G orbital. You have studied that in complex chemistry. Now the remaining two are dx square minus y square and dz square. This x square minus y square we observe by rotating as if this dxy is rotated through 45 degree in the xy plane. Then what happens? All these lobes fall on the axis, isn't it? They fall on the xy axis. So it remains on this plane. Okay, these two are in the same plane. dxy and dx square minus y square are the two d orbitals that remain in the same plane at an angular difference of 45 degree. Okay, so this is an axial orbital, and dz square is having the specialities that it is entirely different from the remaining four in structure. It has only two lobes and a donut-shaped ring in the xy plane. The other two lobes, remain in the z-axis. So that's about it. These two are axial orbitals. Okay. So they are axial orbital and they are designated spectrochemically as EG orbital, as we have studied in complex chemistry. Now we will go through the options. In the atom, all the 5 3D orbitals are equal in energy in free state. Yeah. When not influenced by any other external circumstances, magnetic or electric circumstances, all the 5 d orbitals have the same, all the 5 d orbitals have the same energy. I didn't mean 5d orbital, whether it is 3d orbital, 4d, 5d, 6d, whichever d orbital, all the 5 orbitals in that subshell, d subshell, will have same energy. That's why we call them degenerate orbital. It is valid also for 3d orbital. So statement 1 is correct. The shapes of dxy, dyz and dxz orbitals are similar to each other, and dx square minus y square and dz square are all similar to each other. That is wrong. This is true. First part is correct. Their shapes are identical, but here shapes are not identical. So that statement is incorrect. Third, all the 5d orbitals are different in size when compared to the respective 4d orbital. That's quite natural. Compared to 4d orbital, all the 5d orbitals will be bigger in size. When they are dxy is compared with the dxy, dyz is like that. If you compare all the 5d orbitals will be bigger than all the 5 4d orbitals. Okay, last. All the 5 4d orbitals have shape similar to respective 3d orbital. But shape will be the same. That is not only for 4d and 3d. For all d orbitals, when you compare identical orbital, they will have the same shape. But sizes will keep on increasing from 3d, 4d, 5d, 6d in that order. Okay. So now we come to the conclusion that for question number 76, 2 is the answer. Second statement, where it is wrongly stated that dx square minus y square and dz square have the same shape or structure. Question number 77. It is from periodic properties of elements because it is related to the naming of an element. When it is not allotted, UPC doesn't have allotted a name, it is numerically named. See, atomic number is 119. So, how to name it numerically? 0 is represented by the phrase nil, 1 by un, 2 by, 3 by tri, 4 by quad, 5 by pent, 6 by hex, 7 by hept, 8 by oct, and 9 by ennium. Not non. Non comes in organic chemistry for 9. But here it is n. So what its name? Un standing for 1. Again un standing for another 1. Ennium. Unennium. Unennium. U-U-E. So until its name is finalized by a UPSC, it will be called unennium. Option 3 in the question paper. Okay. Now, question number 78. It's also a statement type question. Statement 1. The boiling points of aldehydes and ketones are higher than hydrocarbons of comparable molecular masses because of weak molecular association in aldehyde and ketones due to dipole-dipole interactions. Okay. See, whenever we compare boiling point, we have to take different molecules of comparable molecular masses because molecular mass is also another factor which have a decisive role in determining the boiling point. So only when we compare, we take molecules of comparable molecular masses, we can assess that this is being more polar, has a higher boiling point. This is of having a less polarity, have a lower boiling point. So to make the effect of molecular masses neutral, change in molecular masses neutral, we have to take molecules of comparable molecular masses. Now, if we are comparing the boiling points of hydrocarbons and aldehyde and ketone of comparable molecular masses, then the reason for the difference in boiling point will be solely due to the difference in the polar nature. Yeah. Now we read the statement again. The boiling points of aldehydes and ketones are higher than hydrocarbons of comparable molecular masses because weak molecular association in aldehyde and ketone due to dipole-dipole interaction. It's a fact that aldehydes and ketones are more polar than hydrocarbons due to the polar carbonyl group in both of them. So, the molecules being dipolar, there will be dipole-dipole attraction among the molecules of aldehydes as well as ketones. Whereas, hydrocarbons are nearly non-polar and in case of most of them, the interaction will be even weaker induced dipole interaction. Here in the case of carbonyl compound, it is permanent dipole interaction. So, we may assess that aldehydes and ketones have higher boiling point than hydrocarbons due to comparatively strong dipole-dipole interaction. So, this statement can be taken as a correct statement. Of course, it creates some doubt since the word weak is used there. Probably they mean the dipole-dipole interaction is a weak force in that sense only. Statement 1, the boiling point of aldehydes and ketones are higher than hydrocarbons of comparable molecular masses because of the weak molecular association in aldehyde and ketone due to dipole-dipole interaction. This statement is prone more to be correct than to be incorrect. So we decide. I am doubtful only just because the word weak is used. Do they mean it is weaker? If they mean weaker than the hydrocarbon molecular interaction, then the statement is wrong. If they simply say dipole-dipole interactions are generally weak, that's okay, then the statement is correct. For the time being, we take that to be a correct statement. Now go to the statement 2. The boiling points of aldehydes and ketones are lower than alcohols of similar molecular masses due to absence of hydrogen bonding. That is very much correct. See, we know in aldehyde and ketone, normal aldehydes and ketone, there is no hydrogen bonding, intermolecular hydrogen bonding. But in alcohol, we know there is hydrogen bonding. And we also know that hydrogen bonding forces are stronger than mere dipole-dipole interaction. So, naturally, the boiling point of alcohol will be greater than aldehydes and ketones, the latter having no hydrogen bonding. So, the statement 2, I read again, the boiling points of aldehydes and ketones are lower than the alcohols of similar molecular masses due to absence of hydrogen bonding. That is a correct statement. So, 90% chance both statements are correct. That is, both statement 1 and 2 are correct. That is, most probable answer for 78 is 3. A small 10% chance statement 1 is incorrect. Statement 1 is incorrect. Statement 2 is correct. That is, 2 has a 10% possibility I am resolving. See, these are the problems of statements. Some statements can be interpreted in different ways. Only the one who prepared the question can say, I mean this. So actually, such a doubtful question should have been avoided in entrance questions, so that they are not a clear test for the intelligence of the student. They are not a clear test to verify the intelligence, because certain sentences can be interpreted in different ways. Such questions should have been avoided, but it is not done here. Okay. Question number 79. You can say this question is from basic concepts of chemistry because it's a numerical problem based on masses of reactants and products, etc. What mass of 95% pure calcium carbonate will be required to neutralize 50 ml 0.5 molar HCl solution according to the following reaction? CaCO3 plus 2 HCl giving CaCl2 plus CO2 plus H2. Okay. See, look at this equation. As per this equation, 2 mole HCl completely react with 1 mole calcium carbonate. Agreed. 2 mole react with 1 mole. Now read the question. In the question, we are interested in the mass of calcium carbonate. So, I can write 1 mole is 100 gram. 2 mole, let it remain as 2 mole. Don't convert that to mass because in the question that is expressed in terms of moles. 2 mole requires 100 gram. In that case, how many moles are present here? How many moles of acid is taken here? Number of moles is equal to molarity into volume. So, n, small n is equal to number of moles, small n, isn't it? Small n is equal to mv is equal to molarity 0.5, volume 50 ml or 50 by 1000 liter. Okay. So, here we have to use volume in liter only. So, 50 by 1000. So, you get 0.025 mole. Now, we want to know 0.025 mole requires how much mass of calcium carbonate. So, 2 mole, 100 gram. Therefore, 0.025 mole, how much gram? 2 moles require 100 gram. In that case, 0.025 mole, how much gram? That upon simplification gives you 1.25 gram pure calcium carbonate. So, if the calcium carbonate were pure, our answer would have been 1.25 gram pure calcium carbonate. But here it is only 95% pure. So, we want the actual mass to be taken in this particular situation. See, therefore mass calcium carbonate when it is 95% pure. See, listen carefully. If you want 95 gram pure calcium carbonate, you have to take 100 gram impure sample. If you want 95 gram pure calcium carbonate, you have to take 100 gram impure sample. In that case, to get 1.25 gram pure calcium carbonate, what actual mass has to be taken? So the substitution comes like this. You have to remember, here you are not multiplying with the 95 by 100, but 100 by 95. If you think, it will come only this way. So the value must be greater than 1.25 because we need 1.25 gram pure. So it will have some impurity also. So the actual mass you take will be slightly more than that. That you get only by multiplying with 100 by 95. Then you get a value very close to 1.32. Then your answer is 4. Okay. Next, question number 80. It is a matching type question. Column list 1 with list 2. Column 1 with column 2. List 1 with list 2. In column list 1, we have certain metals as well as KOH. In the second list, some properties. This question comes from alkali metal because most of the properties mentioned are from that S block elements chapter, first year. Lithium, sodium, potassium hydroxide, cesium on left hand side. Then upon the right hand side, you have absorbent of carbon dioxide, electrochemical cell, coolant in fast breeder reactor, photoelectric cells. See, we know, lithium, sodium, cesium, all these can be used in electrochemical cell. So if you, at the first verification, you feel that lithium can be cross-matched, sodium can be cross-matched, cesium can be cross-matched with the electrochemical cell. So we may not be able to take a decision immediately. Then sodium. If you verify the right hand side, so only sodium or potassium or a mixture of sodium and potassium are used as a coolant in nuclear reactors and fast breeder reactors. So sodium now reserved for coolant in fast breeder reactors. Then KOH. We know potassium hydroxide can absorb the acidic oxide carbon dioxide, isn't it? KOH can absorb the acidic oxide carbon dioxide as per the equation 2KOH plus CO2 giving K2CO3 plus H2O. Okay, so KOH can be matched with the absorbent for CO2. The base absorbs the acidic gas CO2. That's why if you keep a concentrated KOH solution open for long, a solid crust will be formed on the surface, which is K2CO3. Okay, it may later dissolve, but immediately there will be a crust formed. Okay, cesium. We know only cesium can be used in photochemical cells. Right? So we can match cesium with the photochemical cell. Now for lithium, only lithium can be cross-matched with the electrochemical cell. So our first confusion is now over because sodium goes for coolant and cesium went for photochemical cells. So photovoltaic cells. So this is the cross-matching A, B, C, D, 2, 3, 1, 4. That cross-matching is valid for option 2 there. Our answer for question number 80 is 2. The next question number 81. It is from kinetics, a graph-based problem. See, here they have given a general graph y on y-axis and x on x-axis, which is a straight line parallel to x-axis. And in the options they have given such a graph can be a particular graph for zero order, a particular graph for first order. 4 combinations are given, in which combination both for zero order and first order the given statement is correct. That is what we have to verify. You will understand more when we explain. See, for zero order, for first order. In the first option they are saying it can be rate versus concentration of zero order. We know for zero order, even when concentration change, rate remains a constant. So this graph is valid for zero order. On the other side, for the first order, such a graph, what they say, half-life, T-half versus concentration. We know for a first order reaction, even when concentration changes, half-life will not change. That remains a constant. So here also it is correct. So it is valid for both the mentioned graphs of zero order and the mentioned graph of first order. So since both are correct here, in the remaining options, either one must be wrong or both must be wrong. We will verify. In the second option, for zero order, rate versus concentration. Even when concentration changes, rate remains a constant. That is correct. Say, here, when on x-axis T-half aligned parallel to x-axis means half-life changes. Then you don't have to look what is on y-axis. For first order half-life, for a given particular reaction, half-life is independent of the initial concentration, etc. So since here half-life is shown to change continuously, it is meaningless. So this is wrong. So in this pair, one is correct, other is wrong, we cannot accept. The third case, concentration versus time. When time changes, concentration is remaining constant. That is not the case. It is wrong. When time changes, concentration also changes, but the rate is remaining constant for zero order. And concentration is not remaining constant. So this is wrong. What about the other side? Concentration T-half. Even when concentration changes, T-half remains unchanged. Same thing. So it is correct. Correct. But one for zero order it is wrong. For first order it is correct. So as I net it is wrong. And the last combination, concentration versus time. When time changes, concentration remains unchanged. Same. So this also is wrong. What on the other side? When concentration changes, rate constant remains same. That is true. Even when concentration changes, rate is changing, but not rate. First order, even when concentration changing, for first order reaction, when concentration changes, rate also changes, but rate constant will not change. That is indicated here. Concentration changing, but rate constant remaining the same. So on this part it is correct, but on this part it is wrong. So except the option 1, in all the remaining 3 cases, only one is correct, other is wrong. So our answer for the question number 81 is option 1 is our answer. Hope you understood that. Okay. Now question number 82. It is based on interhalogens. So it is definitely a question from P Block Element second year section of halogens. Okay. It is an assertion reason type question. Assertion given is ICl, iodine monochloride, is more reactive than I2. Reason, ICl bond is weaker than I bond. Okay. Yeah, it is true. ICl is more reactive than I2. You may say that ICl bond easily breaks than the breaking of I2. Easy to break ICl than I2 bond. Actually, ICl is more reactive than both the I2 and the Cl2. Since in ICl molecule there is an electronegativity difference, it is easy to break them. That makes the ICl more reactive than I2 and Cl2. Of course, interhalogens are, any interhalogen is less reactive than fluorine because fluorine is the most reactive. The fluorine bond is easy to break due to the electron cloud repulsion between the two fluorine atoms, even though they are non-polar. So fluorine is the most reactive. It is the most electronegative element also. It is the most reactive element also, even when compared even with the any interhalogen. That you have to remember. So here both statements and assertion as well as reason are correct, and reason correctly explain why the statement of assertion is meaningful. So our particular option here 3. One thing you have to take care while you verify with reference to different versions of question. In NEET question paper, as you know, not only the question number but the options are changed in order. Options have different orders in different question papers. So you have to be in different version. Options have different order. So you have to take care of that also. So you have to don't think, focus on 1, 2, 3, 4. you see which option is giving the correct explanation because of this reason. Okay, so there is shuffling of options also. Okay. Here our answer is 3 in this S4 version. S4 version option is 3. The next question is from chemical bonding and molecular structures. The question is from molecular orbital theory. Here they have given 4 options and you have to identify the wrong statement. Okay. The first statement, H2 plus ion has 1 electron. Correct. H2 molecule is having 2 electrons. So H2 plus, that is unipositive hydrogen diatom or molecular hydrogen ion. Unipositive hydrogen diatom has only 1 electron since 1 electron has been removed. That is true. Then O2 plus is diamagnetic. Yeah, that is wrong. O2 plus is having 1 unpaired electron and it is paramagnetic. If you go to the details, if you consider the 5 species O2 plus, then O2 plus, then O2, then O2 minus, then O2 minus. You are adding 1 electron in succession. You know O2 plus and O2 minus. The 2 extremes are diamagnetic because they don't have any unpaired electron. But the 3 in between cases, O2 plus, O2 and O2 minus, all these 3 are paramagnetic. Why? Because O2 plus and O2 minus are having 1 unpaired electron and O2, neutral O2 molecule is having 2 unpaired electrons. So these 3 are paramagnetic. So to extreme dia, the 3 in between cases para. So this statement is wrong. Option 3, O2 plus, in the option 3 they have given the bond orders of some species like O2 plus they have given 2.5, O2 they have given 2, O2 minus they have given 1.5, O2 2 minus they have given 1. Are they correct? We will check. See, for these species, the respective bond orders are decreasing from 3 to 1. How? O2 2 plus 3. Then O2 plus 2.5. O2 2. O2 minus 1.5. O2 2 minus 1. 0.5 is regularly decreasing from one species to the next species until 3 becomes 1. And if you cross check, this data given here is correct. So option 3 is correct. And lastly, they say option 4. What do they say? C2 molecule has 4 electrons in the 2 degenerate pi molecular orbitals. What is the electronic configuration of C2? C2 is having 6 plus 6, 12 electrons. Its electronic configuration 6s2, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then comes the pair of degenerate pi orbital, pi to px and pi to py. Both of them have 2 electrons. So it is correct to say there are 4 pi electrons. 4 pi electrons, and so that statement is correct. This also make C2 molecule diamagnetic. Okay. So our answer for question number 83 is option 2, which is wrong. Okay. Now question number 85. It is from electrochemistry and based on electrochemical series, the reactivity series. In this question, they have given SRP values of certain half cells, metal half cells, and you are asked to predict which all reactions SRP values of set of on the basis standard electrode potential. Predict which of the following reaction cannot occur, not can occur, cannot occur. See, the first thing we have to do is arrange the half cells in their increasing or decreasing order of SRP value, either in mind or in page. Here I have written on the page the SRP values in the increasing order, not as such in the given question. That may lead to more error. So first we rearrange them in such a way that the values are regularly increasing. Minus 0.76, minus 0.44, plus 0.34, plus 0.80. Then arrange the half cell in accordance with the value. Then zinc, iron, copper, silver. See, down the group SRP values are increasing. SRP value increase means reduction tendency increase. For cation, metals, ion, the tendency to become metal is increasing. That means reactivity of metals are decreasing. That's why they want to go back to their metallic state from the ionic state. So down the group, decreasing reactivity of metals. Metal reactivity is decreasing down the group, or non-metallic property is increasing. Okay. So for that reason, if you make cell between any two half cell, the lower one with the higher SRP value will act as cathode. The upper one with the lower SRP value will act as anode undergoing oxidation. Okay. So for any pair, lower one is cathode, upper one is anode. So again, in ordinary chemical reaction, a metal above in the series can replace a metal below from the compound of the latter. A metal above, which is more reactive, can displace a metal below, which is less reactive, from the compound of the less reactive metal. So now we can easily verify. All these things must go through your mind before you answer the question. I have just written all these things. First reaction they have given Fe2 plus Zn, Zn2 plus Fe. As per this reaction, zinc is more reactive. Zinc is more reactive. That's why it is reducing Fe2 plus to Fe. Is that correct? Yeah. Zinc is at the top. So among all these metals, zinc is more reactive. So this reaction can happen. So that is not the answer. Okay. The second one, Cu2 plus 2Ag giving Cu. See, I have avoided sulfate iode. It is not at all required for explaining this question. Okay. See, I have, for instance, FeSO4, I used only Fe2 plus. CuSO4, I used only Cu2 plus. Cu2 plus 2Ag giving Cu plus 2Ag plus. As per this equation, which is more reactive? Silver is more reactive, isn't it? Because it is donating its electron to copper ion. Copper is less reactive. But as per this diagram, copper is more reactive than silver. As per this reaction, silver is more reactive than copper. So this is wrong. So probably that is our answer. Next step. Cu2 plus Zn giving Cu plus Zn2 plus. As per this reaction, zinc is more reactive because it is releasing electron. Yeah, zinc is at the top. So zinc is more reactive. It is correct. Again, Cu2 plus Fe giving Cu plus Fe2 plus. As per this reaction, iron is more reactive than copper because iron is releasing electron. Yeah, true. Fe2 plus is above, Fe is above Cu. So this is also true. So our answer for this question 85 is 2. Hope you understood that. Now question number 85. See, this question is based on chirality, means related to optical isomerism, and we study optical isomerism in second year haloalkane, haloarine. So this question can be said to be from chapter 10 or the haloalkane and haloarines. Okay. The incorrect statement regarding chirality. Enantiomers are superimposable mirror images on each other. Enantiomers are a pair of optical isomers of the same compound which are related as object and mirror image, which are non-superimposable. For example, look at this formula. Let this be a chiral carbon, A, B, D, E. It's a mirror image, A, B, D, E. Look at that. It appears like mirror image. You cannot superimpose them. See, if you try to attempt to superimpose, any two bonds can be exact, any two desired bonds can be exactly superimposed. For example, you can superimpose A with the A and say E with the E. Then what happens? B will be embossed on D and D will be embossed on B. So perfect superimposition is not possible. Only two bonds are selectively superimposed, the other two are cross-imposed. So any two. So you may superimpose B and D on B and D of this. Then A will be on D and D will be on A. So perfect superimposition is not possible. That's why we say that they are non-superimposable. Hope you understood that. So very statement 1 is wrong. Since incorrect statement is as, we expect that to be our answer, 85-1. Before that, let's verify the other options. Racemic mixtures have zero optical rotation. Actually, there are some, racemization means the planar sp2 hybridized species is attracted from the nucleophile with the equal possibility from both sides. So you get to 50% dextroform, 50% levoform. But in many other questions, even in NEET, they say that it need not be 50-50 because at least some molecule may involve SN2 reaction. So only when it is ideal 100% SN1 reaction, you get such an answer. There are other questions, as I mentioned you, where they say that it is not 50%. If you select in such questions, if you select 50%, you will get negative mark. Because one of the form will be more, 60%, 40% like that it will become. Because some molecule some molecule undergo SN2 and involves inversion. So either of the form will be more in amount. But here we have to assume that both the ideal SN1 reaction, 50% dextro, 50% levo, then only these two become correct. Since this is a perfect incorrect answer, this has to be a correct answer. That's the only way to conclude that. Then SN1 reaction, racemic mixture has zero optical rotation. As I told you, if the mixture is 50%, sure, that will be optically inactive due to external compensation. What is meant by external compensation? Because at the molecular level they are optically active, but being present in equal amount, they cancel one another. That's why it is called external compensation. Is there any internal compensation? Yeah, in the case of molecule with the 2 chiral carbon, as in the case of tartaric acid, if optical rotation at the one end is cancelled by the optical rotation of the other end, the very molecule will be optically inactive. Such molecules are called meso. So meso variety involve internal compensation of optical rotation. Here it is not internal compensation, it is external compensation because two molecules rotate in opposite direction. In the other case, in the same molecule, one end rotate in one direction, the other end rotate in opposite direction. That's why it is called internal compensation. So racemic mixture has zero optical rotation, external compensation is correct. SN1 reaction yield 1-1 mixture of both energies. That's why I told you it is not 50% act in reality. Only when the reaction is ideally SN1 and then only 50% one form and 50% other. So we have to accept here, since we are sure about this answer, we have to accept this as a correct statement. And the fourth statement, what do they say? The product obtained by SN2 reaction of haloalkane having a chirality at the reactive site shows inversion of configuration. The sentence is now ideal symbol. This is a compound where this carbon is chiral because all the 4 attachments are different. R1, R2, R3 and Cl. OH minus is attacking from rear. So it undergo Walden inversion. Molecule get inverted. It become OH in the opposite direction. So optical rotation is, its configuration is inverted, isn't it? So that statement is correct. The product obtained by SN2 reaction of haloalkane having a chirality at the reactive site shows inversion of configuration. That is also another correct statement. So we definitely conclude that for question number 85, answer is 1. Now we have question number 86. We start section B with the 15 questions where you have options to answer 10 questions. Okay. See, 86th question is cross-matching type. We have some ores on the left-hand side. You have to match it with the correct composition. The left-hand side we have hematite, magnetite, calamine and kaolinite. On the other side, after cross-matching we get hematite Fe2O3, magnetite Fe3O4, calamine zinc carbonate, and kaolinite it is a hydroxysilicate of aluminium. Al2OH4, Si2O8, it is clay. So that's the proper combination. A versus 3, B versus 1, C versus 2, and D versus 4. Such a combination that is 3, 1, 2, 4. 3, 1, 2, 4 comes in option 4. So 4 is the answer for question number 86. 4. Okay. Now we have the 87th question. Here it is based on aldol condensation. Whether it is aldehyde or ketone, generally they are called aldol condensation. It can be ketonic condensation. Ketone condensation are also considered under the main heading aldol condensation. Okay. We know when carbonyl compounds react containing alpha hydrogen, that is hydrogen on the adjacent carbon to carbonyl group, it undergoes aldol reaction. First it forms an aldol, which may further undergo alpha beta dehydration process to give alpha beta unsaturated aldehyde or ketone. If only the first part of the reaction, that is aldol formation alone is involved, we don't call it aldol condensation. We call it aldol condensation only when the second part of the reaction is also completed, that you get an alpha beta unsaturated aldehyde or ketone, then only it is called aldol condensation. Otherwise we simply call it aldol reaction. Okay. When both stages are completed, it is called aldol condensation. Okay. Look here. Here we are treating two different ketones in this particular condensation process. One is propanol and the other is 2-pentanol. Okay. See, condensation can happen in different ways. This molecule can condense with itself. It's a normal condensation process. This molecule can condense with itself. It is also a normal condensation. Other possibilities are this can condense with this and this molecule condense with this. So there are large number of possibilities. See, since the alpha carbon on propanol, two alpha carbon on propanol are identical, whether condensation happen with respect to this methyl group or this methyl group, the products are not going to be different. Okay. On the other hand, look at this compound. This alpha carbon and this alpha carbon are in different situation. So we get two different condensation product when this carbon group is involved and this carbon group is involved. So we will see different possibility of condensation. Also look at the color concepts we have used. It will make the idea more easily understood. Here for propanol I have used the blue color and for pentanol I have used red color. First we will consider normal, again this methyl group and this methyl group being identical, I have named them both one. This carbonyl group in propanol is called named A. This methyl group and this methylene group being different, I have named them 2 and 3, and this carbonyl group I have named B. First we will consider normal condensation, that is between identical molecule. Suppose this molecule is condensing with another molecule of this. How we can write 1 versus A? Not within the same molecule, one propanol molecule with A of another propanol molecule. Normal condensation, as if we have taken only propanol for condensation. So this or this CH3 group will condense with the carbonyl group of the second propanol molecule. Then we can write it. Look here, this is the first propanol molecule. It's a 2 hydrogen, condenses with the CO of the second propanol molecule, resulting in a double bond. So we can, it was like this, CHH2, CH3 it was, 2 hydrogen from this and the carbonyls O, they together eliminated as a water molecule. So this is the propanone versus propanone condensation molecule. So one product is this. Now think about second case. 2 versus B means pentanone is condensing with another molecule of pentanone. Here methyl group, not methylene group, is involved in condensation. So I am using red color only because both molecules are pentanone. So I am writing the first molecule. Since this CH3 is condensing, I am starting writing from this side to this side. Look, CH3, CH2, CH2, then CO, then next last CH3, CH, double bond. Now I start writing the second molecule. Its carbonyl group is condensed, so C double bond O is gone. Now this CH3 is this CH3, remaining CH2, CH2, CH3. Okay, that is the second case, 2 versus B. Here we have to consider 3 versus B. 3 versus B means this methylene group condenses with another 2-pentanone molecule. So I start writing with the this molecule with the CH2 at the terminal. So look here. This is the CH2. Actually, I use this way. This thing. I'm sorry. Yeah. Look here. This case 3 versus B. 3 versus B. That is 3 versus B of another molecule. So I start writing the first molecule CH3 CO CH2. CH3 CO CH2. That condenses. The remaining part of CH2 CH3 is written upward. CH2 CH3. Second molecule is carbonyl group. C double bond O. And it will have one CH3 downward and a CH2 CH2 CH3 in that direction. So that is the third case. These three are the normal condensation products with the atmosphere. It is a bit difficult. Now we have cross condensation reaction. How cross condensation reaction takes place? It's a carbonyl can condense with it's a methyl or methylene group, or it's a methyl group condense with it's a carbonyl group. These are the other possibility. Cross condensation. First one there. Fourth one. Total number fourth one. 1 versus B. It's a methyl group condenses with it's a carbonyl group. So I start writing with this compound CH3COCH methyl group. Now I have to start writing the red color carbonyl group. CO, it's a carbonyl group is involved. So C double bond O. It's a CH2, it's a CH3. This CH3 is shown here, and this remaining CH2, CH2, CH3 is shown that way. So it is 1 versus B. Now we have this condensing with this and this condensing with this cross condensation reaction. So now next one 2 versus A. 2 versus A. I start writing 2. So CH3 might be at the terminal. So I start writing from this way towards this end. CH3, CH2, CH2, CO, CH. Now I start writing this compound. It's a carbonyl group. Condenses. It's a 2CH3 group written like that. Finally we have 3 versus A. Oh, 3 versus A. So I have to write this first. So I start writing. Look here. I start writing here. Here also I start writing from here. CH3, CH2. This C is condensing. So I stop. And the remaining part I write upward. COCH3. Okay. Then now I start writing this. Double bond C, CH3, CH3. Okay. So 6 possibilities are there. Probably you must be a bit confused. Please pause the video and slowly go through it again. You will understand that. So maximum possibility is 8. When 8 possibilities come, when this is see, this is a unsymmetrical ketone, this is a symmetrical ketone. If this is also an unsymmetrical ketone like 2-butanol, you will get 2 into 4, 8 possibilities. Here we have only 6 possibilities. 1, 2, 3, 4, 5, 6. Because one is symmetrical, even though other is unsymmetrical. Hope you understood that. Okay. Now we have to cross match with the answers given in the question. We have to, in the question it is asked which will not be formed. Okay. Cross checking is a bit difficult. Before cross checking I will tell one thing. If this couples with this condenses with this, there will be 6 carbon. So in this case the molecule has 6 carbon. When this condenses with this, 5 into 5, 10 carbons will be there in the second case. Third case also, this is condensing with its own molecule, so 10 carbon. Now the remaining 3 are cross condensation. So 3 plus 5, 8 carbon. In the remaining 3 cases, we have 8 carbon, 8 carbon, 8 carbon. Okay. Now you take the question paper. See, look at the 4 options given there. In the first case, check how many carbon atoms are there. 1, 2, 3, 4, 5, 6, 7, 8 carbons are there. So, the first one will be anyone among these 3. Okay. Second option, 2. 1, 2, 3, 4, 5, 6, 7, 8. So second option also comes from here. Third option, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 carbon. So that must be this. Only one case it is 6 carbon. And the fourth one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbon. So the fourth one must be either this or this. But one is not present because there is one negative answer. And now I am asking you, please check. The first one given there. First one, if you cross check, its structure is this. Look the first one. CS3, CH2, CH2. CS3, CH2, CH2. It is like this. CS3, CH2, CH2. The next carbon is having one methyl group and one double bond. Then CO, CS3. So this is the first option given. So that product will be formed. Now look at the second one. I have already verified. The second one is the last one with the 8 carbon case. Look, 1, 2, 3, 4, 5, 7. It is having only 1, 2, 3, 4, 5, 6, 7, 8 carbon. So you cross verify only the airs. So you have to verify only this and this. This is already 1. So either this or this. If you examine, you will see this is the 2. How? See 2 CS3 groups. Then 1 carbon with a double bond. Yes. Now, we are drawing in the opposite direction. Then CO CS3. Also CS2 CS3. Please check. This is 2. That is 2. Now third one. See if you verify. Third one, 1, 2, 3, 4, 5, 6 carbon. There is only one case with the 6 carbon. So this must be that. We will check that CS3, CO, CS double bond C, CS3, CS3. Yeah, that's correct. So the fourth one, that will not be there. That should not be there, isn't it? We will check. Fourth one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbon. We have to prove that structure is neither this nor this because only 2 cases we have 10 carbon. You verify. See, in this given structure there are a double bond to which 2 ethyl groups are attached. A double bond with the 2 ethyl group attached to that double bond on one side. Neither of this structure have 2 ethyl group. In both these cases we have 1 methyl and 1 propyl group. So that structure which is 4 is not given. Will not be a possibility. So we have concluded that option 4 is the answer. Oh, it's a bit tedious game, I must say. So for this question number 87, 4 is the answer. Okay. Hope you understood that. Okay. The next question from solid state chemistry. You have to get the answer by using the equation for finding density of the metal. We know density D is equal to gram atomic mass into cell content Z divided by Avogadro number into edge length cube, isn't it? So in this particular problem, we want atomic mass of the metal copper. So if we rearrange the equation, Wm is equal to D into Avogadro number into edge length cube by Z. Now you substitute. 8.92 is the given density. Avogadro number we will take 6 into 10 power of 23. And the edge length they have given in centimeter, so you don't have to convert that into centimeter. 3.608 we take 3.6 into 10 power of minus 8 cube by. Being FCC, its cell content is 4. Denominator is 4. See, that is not a thing that you can easily find by simple arithmetic. To be frank, I used calculator and I got the the part other than 10's power gives on calculation 624.2. Then you have another into 10 power of 23, another 10 power of minus 24. Then you get a 62.4 gram per mole, and that answer is closest to answer 363.1. So we accept C3 as the answer for this question. Okay. Next question. It is based on ozonolysis of alkene. So it must be from the chapter hydrocarbon first year. Okay. What the question says, compound X on reaction with the O3 followed by Zn bar H2O treatment gives formaldehyde and 2-methyl propanol as the products. The reactant, the compound X is. You are given the product of ozonolysis from which you have to identify the original alkene. What are the products they mentioned? The products are formaldehyde, HCHO, plus 2-methyl propanol. 2-methyl propanol or propanol. You know how to get the parent alkene. You know where these carbonyl groups are there, there is the double bond. So it is very easy. So you simply wipe out the carbonyl group and directly connect the bond. You know that. So this will be the compound. That is CH2 double bond CH, CH, CS3, CS3. Isn't it? So what is IUPAC name? It is but1ene. Then it is having a CH3 on the third carbon. You have to count from this end. So it is 3-methyl but1ene. That is option 3 for question number 89. 3 is the answer for question number 89. Okay. The next question, question number 90. If radius of second Bohr orbit of the helium plus He plus ion is 105.8 picometer, what is the radius of the third Bohr orbit of Li2 plus ion? Comparison with that. See, we know the basic equation for radius of single electron species like He plus Li2 plus etc. that is Bohr radius is given by the relation R is equal to 5.29 into 10 to the power minus 11 n square by Z meter. Okay. Or you can say radius is proportional to n square by Z. Now we take the ratio of the radii of lithium 2 plus and He plus. R Li3 plus third orbit by R He plus second orbit is equal to n square for lithium, n is third, 3 square by nuclear charge is 3, divided by helium, n second shell, so 2 square by nuclear charge 2 is equal to 3 by 2. Therefore, R Li plus third orbit, this one, is equal to your cross multiplying. R He plus into second into 3 by 2. The given value is 105.8 picometer into 3 by 2, which gives you 158.7 picometer. This question evidently from the chapter Atomic Structure, first year, third chapter. Okay. Not third chapter, second chapter. Okay. Question number 91. In neutral or faintly alkaline medium, KMnO4 oxidizes iodide into iodate. The change in oxidation state of the manganese in this reaction is from. Different options are given. This question can be either from redox reaction or potassium permanganate that comes in D block elements, D and F block elements, that chapter. Okay. See, for this you must know this equation by heart. 2MnO4 minus plus I minus plus H2O giving 2MnO2 plus IO3 minus plus 2OH minus. That equation. Only if you are familiar with that equation, you can answer this question. Here, oxidation state of manganese changes from plus 7 to plus 4 in MnO2. So, your answer is 3. Plus 7 to plus 4 for this question. Okay. Question number 92. Statement 1. In Lucas test, primary, secondary, and so this question is from alcohol and phenol. In Lucas test, primary, secondary, and tertiary alcohols are distinguished on the basis of their reactivity with the concentrated HCl ZnCl2 mixture known as Lucas reagent. We know that ROH upon reaction with the nitrogen chloride, concentrated HCl become RCl. Okay. HCl known as Lucas reagent. Primary alcohols are most reactive and immediately produce turbidity at room temperature on reaction with the Lucas reagent. That's the second statement. We know that primaries, if you consider the reactivity of primary, secondary and tertiary alcohol, we know that a tertiary alcohol gives immediate turbidity, whereas secondary alcohol take 5 to 10 minutes to produce the turbidity, whereas secondary alcohol takes 5 to 10 minutes to produce the turbidity, whereas primary alcohol do not give turbidity at all at the room temperature. Primary alcohol does not produce turbidity at the room temperature, means primary alcohol is the least reactive, tertiary alcohol is the most reactive, secondary alcohol comes then, last comes primary alcohol. Why it become turbid? Even though the alcohols are somewhat soluble in the water content of the Lucas reagent, in the case of tertiary alcohol, whenever it changes to chloride, its solubility decreases. Alcohol is more soluble, whereas the corresponding chloride is less soluble. Since tertiary alcohol reacts and gets converted to tertiary halide, there is an immediate turbidity because of the lack of solubility of the chloride. In the case of secondary alcohol, it takes up to 5 to 10 minutes, so turbidity appears slowly. In the case of primary alcohol, at room temperature there is no reaction, only if the mixture is heated the reaction is there. So at room temperature, since it remains as alcohol which is nearly soluble in water, no turbidity appears at all. The reagent is called a Lucas reagent and such reactions are called Greuze reaction. G-R-O-O-V, Greuze reaction. And this is Lucas reagent. This is based on the solubility difference of an alcohol and the corresponding chloride. Okay. So here, if you read the statements again, in Lucas test, primary, secondary and tertiary alcohols are distinguished on the basis of the reactivity to the concentrated HCl and zinc chloride, known as Lucas reagent. That statement is correct. Primary alcohols are most reactive and immediately produce turbidity at room temperature on reaction with the Lucas reagent. We know that's a wrong statement. So statement 1 is correct, statement 2 is wrong. That option is option 1. Statement 1 is correct, but statement 2 is incorrect. So for question number 92, answer is question number 92, answer is 1. Question number 92, answer is 1. Okay. Next question. This is from chemical equilibrium. Given 3O2 gas reversibly giving 2O3 gas. For the above reaction at 298 Kelvin, Kc is given to be 3 into 10 to the power minus 59. If concentration of O2 at equilibrium is 0.040 molar, then concentration of O3 is dash molar. We directly substitute. Kc is given 3 into 10 to the power minus 59. O3 you have to find out. Square bracket O2 0.04. The first square bracket O3 squared is equal to 3 into 10 to the power minus 59 into 4 into 10 to the power minus 2 the whole cube. Gives you 192 into 10 to the power minus 65. Or after decimal adjustment, 19.2 into 10 to the power minus 64. So that this is, we can easily find the root of minus 64. Okay. So O3, concentration of O3 is equal to under root 19.2 into 10 to the power minus 64. Now we know 4 into 4 is equal to 16. 5 into 5 is 25. 16 and 25. 19.2 comes in between 16 and 25. So we can say root of 19.2, square root of 19.2 will come in between 4 and 5. 4 square is 16, 5 square is 25. So 19.2 comes in between 16 and 25. So we approximate that its value, root of 19.2 comes in between 4 and 5. And root of minus 10 to the power minus 64 is equal to 10 to the power minus 64 by 2 minus 32. So answer will be a value that comes this way. 4 to 5 into 10 to the power minus 32. Such a value is option 3, 4.38 into 10 to the power minus 32. So our answer for question number 93 is 3. Okay. Next question 94. It is from gaseous state or states of matter. A 10 liter flask contains 64 gram of oxygen at 27 degrees Celsius. Assume O2 to behave ideally. The pressure inside the flask in bar is given R value in a unit having bar, that is 0.0831 liter bar per Kelvin per mole. We know pressure is equal to nRT by V, where we can split N as mass by molar mass, W by W. So now we can substitute. Mass taken is 64 gram. R value involving unit of pressure in bar is 0.083. Temperature 298 Kelvin given in the question. Molecular mass of O2 32 and volume of the vessel 10 liter. After simplification you get a 4.952 bar, which corresponds to an answer 2. 94 answer is 2. Very much straightforward question. Next, 95th question. It is from electrochemistry, where you have to use Nernst equation and find the voltage of the given cell. In the question, they have presented the cell reaction nickel solid plus 2 Ag plus, concentration 0.001 molar, giving Ni2 plus 0.001 molar again, and silver solid 2 Ag. If you want, looking at this chemical equation, you can represent the cell also here. Look here. Here Na is becoming Ni2 plus. So anode is Na bar Na2 plus. Its concentration 0.001 molar. Double bar. Okay. Then Ag at the same time Ag plus is becoming Ag. So cathode is Ag plus 0.001 molar Ag. So this is the cell. This is the cell reaction. Now looking at the cell reaction, we can write E cell is going to be E0 cell minus 0.0591 by N. N is the number of electrons involved in the balanced chemical equation. These 2 electrons that is exchanged. So N is 2 log Ni2 plus concentration of Ni2 plus divided by concentration of Ag plus the squared. Okay, that's the equation. Now we can substitute. But in the question there is a mistake. They have wrongly given as the standard cell voltage to be 10 to the power 5 volt. If you compute the standard cell voltage by looking at the SRP list, it will come out to be 1.05. A decimal position has been changed. Only if you use that value 1.05, we get the answer, not otherwise. So this question will be mostly cancelled. Of course, I have completed the problem using the original value of 1.05. 1.05 minus 0.0591 by 2 log 0.001 divided by 0.001 square is equal to 1.05 0.02955 into log 1 by 10 to the power minus 3. 0.001 cancels, or the last term becomes log 10 to the power of 3. Log 10 to the power of 3 is 3. So 1.05 minus 0.02955 into 3. That becomes 1.05 minus 0.08865, which gives you an answer plus 0.96135. That is, out of the given values, 1 will be the answer. But since no data is given wrongly, this question is mostly get cancelled. Okay, we proceed to the next now. Now we have question number 96, organic chemistry. It can be said to be from amine. Okay, chapter amine. We start with the benzonitride or phenyl cyanide. As per the question, we first treat it with the lithium aluminum hydride and water, then with the sodium nitrate and HCl, and finally with the water. You have to identify the final product. Actually, even though they have shown one lithium aluminum hydride comma water, it is wrong. We have to first add to the benzonitride. We first add a lithium aluminum hydride alone. That forms a complex. Then break it with the water. If you directly add a lithium aluminum hydride and water together, they will react among themselves. It will not react with the benzonitride. So first we have to add a lithium aluminum hydride. Then we add a water. Then the nitrile group get converted to a primary amine group, CH2NH2. Through reduction, it becomes CH2NH2. We get a benzyl amine. And now, in the second stage, we are treating it with the NaNO2HCl. Actually, the temperature has to be maintained 0 to 5 degrees Celsius, so that nitrous acid is formed, which convert this to corresponding diazonium chloride. Okay. But we know it is unstable. Even the water present in the mixture gets converted to alcohol. But in the question, it is mentioned 3H2O. So we show that separately. H2O giving you benzyl alcohol plus nitrogen gas plus HCl. So among the given options, the answer is 2. Okay. Now we go to question number 97. For a reaction, for a first order reaction, A giving products, initial concentration of A is 0.1 molar, which becomes 0.001 molar after 5 minutes. The rate constant for the reaction in per minute unit is. See, it's a straight direct problem which makes use of the integrated rate law for the first order reaction. K is equal to 2.03 by T log C0 by Ct. 2.03 by 5 minutes, so 5 log initial concentration 0.1, final concentration 0.001. So 2.03 by 5 log 1 by 100. I'm sorry, log 100. I'm sorry, log 100. So 2.03 by 5 into 2, which gives you nearly 0.92 minutes. 4 is the answer. Okay. Next question. Question number 98. IUPAC naming. We can say it is a question from basic principles of organic chemistry. You can also say from haloalkane, haloarine. You can even say hydrocarbons, etc. Any of these chapters. The IUPAC name of this compound. See, this is the carbon chain. It has 6 carbon. If you number from here, the OH group decides from which side you have to number. 1, 2, third carbon OH comes. OH comes, yeah. If you number from here, 1, 2, 3, 4. Fourth carbon OH comes. So, we keep the minimum number for the locant carbon carrying OH. So, we have to number from this side. Then we name it. We have 1 bromo, then alphabetically 5 chloro comes next. Then alphabetically 4 methyl comes third. Hexane, 3 all. So, 1 bromo, 5 chloro, 4 methyl, hexane 3 all means answer 3. 1 bromo, 5 chloro, 4 methyl, hexane 3 all. 3 is the answer for question number 97. Okay. The next question, it is from coordination complexes. The order of energy absorbed which is responsible for the color of complexes. We know color of complexes results from the DD transition of electron. Okay. The 3 complexes are given of nickel. In one case, we have nickel with the 2 water molecule and the 2 ethylene diamine molecule. In the second, 4 water molecule and only 1 ethylene diamine is a bidentate ligand. So, in the second case, 4 water molecule, 1 ethylene diamine. In the third case, you have all the 3 ethylene diamine. We know ethylene diamine is a strong ligand, a bidentate strong ligand. So, when strong ligands are involved, the bondings become highly stable and excitation of electrons require more energy. So, maximum energy will be absorbed for electron transition in the case where there are 3 ethylene diamine ligands. Then comes the second because there are 2 ethylene diamine ligands. Last come 1 ethylene diamine molecule. So the order is C greater than A greater than B. Ethylene diamine means ethane 1,2-diamine. This. Even though the name has the word ethylene, it doesn't mean it is unsaturated. It is a bidentate ligand. Okay. So it is one of the strong ligand. Okay. So our answer C greater than A greater than B, the order in which energy is absorbed. So this comes as answer 1. Question number 99, answer is 1. Okay. Now we have the last 100 question. This from environmental chemistry. The question is, the pollution due to oxides of sulfur get enhanced due to the presence of A. particulate matter, B. ozone, C. hydrocarbons, D. hydrogen peroxide. Choose the most appropriate answer for the option given below. You can choose from this, which all enhances the pollution due to sulfur and its oxide. See, in our text it is very clearly mentioned that particulate pollutants in atmosphere, then ozone, then hydrogen peroxide, all these help the conversion of SO2 to SO3. SO3 is a more severe pollutant. So, A. particulate pollutant, B. ozone, D. hydrogen peroxide. All these we can directly oxidize sulfur dioxide to sulfur trioxide. This can catalyze the conversion of SO2 to SO3. So these are the 3A, B and D are the options. That is, A, B and D are the materials which helps the conversion of SO2 to SO3, making the pollution due to sulfur compounds more severe. So our answer is the combination of A, B and D, not hydrocarbon. Hydrocarbons are mostly reducing agent. Here what is involved is oxidation. So that combination is option 4. So for our 100th question, the answer is 4. With that, we come to the conclusion of this discussion of the NEET 2022 question paper. Take care. Bye.